and active star-forming regions. The LMC is home to the Tarantula Nebula, 30 Doradus, the most active star-forming region in the local group. This nebula produces clusters that provide critical data on stellar evolution. The LMC also has notable supernova remnants, including SN 1987A, the closest observed supernova in modern history. SN 1980 is an unprecedented opportunity to study the life cycles and how waves in surroundings. The Magellanic Galaxy is composed of both young and old stellar populations, making it a crucial subject for studying galaxy evolution over cosmic timescales. It hosts numerous globular clusters, open clusters, and variable stars, including RR Lyrae and Cepheid variables. These stars play a vital role in calibrating the cosmic distance scale, as their predictable luminosity variations serve as standard candles. This calibration is essential for determining the Hubble constant and refining our understanding of the universe's expansion rate. Research into the structure of the Magellanic System reveals its dynamic interactions with the Milky Way and its smaller companion, the Small Magellanic Cloud, SMC. These gravitational interactions cause tidal distortions and an exchange of gas and stars between the galaxies. The Magellanic Stream, a vast, elongated structure of gas extending from both galaxies. These processes likely contribute to the irregular morphology of this satellite galaxy-related star formation activity. The composition and metallicity of the Magellanic satellite present another area of scientific interest. With a lower metallicity than the Milky Way, it serves as a vessel for studying the conditions of early galaxies in the universe. Its interstellar medium is rich in neutral hydrogen and molecular gas, both fundamental to star formation. Observing its chemical abundance content helps astronomers model the chemical enrichment of galaxies and understand how feedback mechanisms influence their evolution. The Magellanic Neighbor is also central to studies of dark distribution in galaxies. Since its mass is largely dominated by dark matter, it's an opportunity to investigate the properties and behavior of this elusive star. By analyzing its rotation curve, gravitational lensing effects, and tidal interactions, astronomers gain deeper insights into the nature and large-scale distribution of dark matter. Observations from advanced telescopes, including the Hubble Space Telescope, the Atacama Large Millimeter Slender Array, ALMA, and ground-based observatories, have significantly expanded our understanding of this nearby galaxy. Future missions, such as those from the Webb Space Telescope, JWST, promise to uncover even more details. Multi-wavelength studies, from radio waves, continue to reveal the complexities of its structure, active star-forming region dynamic interactions. Beyond its scientific importance, the Magellanic Cloud holds a prominent place in cultural astronomy. Indigenous peoples of the Southern Hemisphere have long incorporated it into their mythologies and cosmologies, often viewing it as a celestial companion, distinct cosmic entity. Its visible naked eye makes it a familiar and awe-inspiring night sky, inspiring awe. As a cornerstone of astrophysical research, the Magellanic Companion bridges our understanding of local galactic processes with the broader context of cosmic evolution. By studying this neighboring galaxy, scientists uncover fundamental mechanisms shaping galaxies and their components, providing a window into the history and future of cosmic structures. The Magellanic stellar system also has a fascinating star formation history. Spectroscopic and photometric studies reveal that it has experienced multiple bursts of star formation over time. be closely linked to its interactions with both the SMC and the Milky Way. Gravitational forces from these interactions likely triggered compressions in its interstellar, leading to intensified star formation. These events unique opportunity to study how galactic interactions shape their evolutionary trajectories. The rotation curve of the Magellanic Disk is another key area of investigation, shedding light on its mass distribution. By measuring the velocities of stars and gas within the galaxy, astronomers infer the presence of dark matter. Observations suggest that, like most galaxies, it possesses a substantial dark matter halo extending far beyond its visible disk. Understanding the characteristics is crucial for unraveling the nature, one of the greatest mysteries in modern astrophysics. The most intriguing aspects of the Magellanic Cluster is its ability to host a diverse array of stellar remnants, dwarfs, neutron stars, and black holes. Its dense star clusters are environments for the formation of such remnants, which offer valuable insights into the final stages of stellar evolution. Observations of X-ray binaries in this galaxy provide critical data on the interaction of compact objects and their scenes, shedding light on the physics of accretion and relativistic jets. Finally, the Magellan's globular clusters are invaluable for studying the early stages of galaxy formation. These ancient structures, among the oldest in the universe, contain stars with extremely low metallicities, providing insight into the conditions that prevailed during the universe's. The distribution clusters also offer clues about the Magellanic satellite's past interactions with other galaxies, helping to reconstruct its orbital history. In the context of stellar evolution, the Magellanic system serves as a natural laboratory for understanding how stars of different masses evolve and reach their final stages. The presence of massive stars, including Wolf-Rayet stars and red supergiants, allows to investigate the processes leading to supernova explosions and the formation of compact remnants like neutron star holes. The Tarantula Nebula, in particular, remains a focal point of study, as it hosts massive stars ever observed, some exceeding 100 solar masses. The Magellanic Galaxy also plays a significant role in our understanding of the cosmic baryon cycle. Observations of its gaseous halo and the Magellanic Stream, a vast ribbon of gas, the LMC and SMC, provide crucial data on how galaxies acquire, retain, and lose gas over time. This process is essential for regulating star formation and shaping galactic evolution. The Magellanic Stream, composed primarily of neutral hydrogen, is believed to have been stripped from these galaxies during past interactions, serving as a potential reservoir of material that may eventually accrete onto the Milky Way. Moreover, the Magellanic Companion provides a unique opportunity to study the interaction between magnetic fields and the interstellar medium. The alignment of dust grains and the polarization of starlight observed within the LMC reveal large-scale magnetic fields that influence gas dynamics and molecular cloud formation. Understanding these processes is crucial for developing comprehensive models of galaxy evolution. The future of research on the Magellanic Nebula holds immense promise, with the advent of next-generation observatories. The James Webb Space Telescope, JWST, will enable astronomers to study its star-forming regions in unprecedented detail, probing the earliest stages of star and planet formation. Meanwhile, radio telescopes such as the Square Kilometre Array, SKA, will map its neutral hydrogen distribution with unparalleled resolution, providing new insights into its gas dynamics and interaction history. based facilities like the telescope will further contribute by resolving within this galaxy precise measurements of their chemical compositions and ages. As our knowledge of the Magellanic cluster deepens, it becomes increasingly clear that this nearby galaxy is central to answering some of the most profound questions in astrophysics. From the nature of dark matter to the mechanisms driving star formation and galaxy interactions, the LMC continues to yield crucial insights into the workings of the universe. The Magellanic Cloud is also an invaluable resource for studying chemical enrichment in galaxies. Its unique metallicity gradient, which varies with distance from its center, offers a window into how heavy elementized and describing the abundance patterns of elements like oxygen, carbon, and iron across different regions. Researchers can reconstruct its history of star formation and supernova activity. These studies are particularly significant for understanding the origins of life-essential elements, such as carbon and oxygen, which dying stars release into the interstellar medium. Another key area of investigation is the LMC's role in galaxy mergers. As it continues interacting with the Milky Way, it gradually loses mass through tidal stripping. This process not only alters the Magellanic satellite structure but also contributes to the formation of stellar streams and the accretion of gas onto the Milky Way. In several billion years, the LMC is predicted to merge with our galaxy, an event that will have profound effects on the Milky Way's structure and dynamics. Studying these interactions in real time offers a unique opportunity to model the physics of a fundamental process in the hierarchical galaxies throughout the universe. Furthermore, the Magellanic Neighbor's position within the local group allows astronomers to investigate how its radiation field impacts the interstellar medium. Intense ultraviolet radiation from young, massive stars in regions like the Tarantula Nebula drives powerful stellar winds that creating intricate structures such as bubbles, shell elements. These features are crucial for understanding feedback mechanisms in galaxies, where energy and momentum from stars regulate star formation by either compressing or dispersing molecular clouds. One of the Magellanic's significant contributions to astrophysics lies in its population of variable stars. Classical Cepheids, for instance, have played a crucial role in refining the cosmos. Their well-established relationship between luminosity and pulsation period provides a highly accurate method for measuring extragalactic distances, ultimately helping to determine the Hubble constant. Observations of these stars have enabled astronomers to achieve some of the most precise measurements of cosmic expansion, significantly reducing uncertainties in our understanding of the universe. This neighboring galaxy also serves as a key benchmark for studying the interaction between dark matter and baryonic matter in low-mass galaxies. Simulations of its evolution within the Milky Way's gravitational field suggest that its dark matter halo may be asymmetric, shaped by tidal forces and past interactions. By comparing observational data, models continue to refine their understanding of dark matter's influence on galactic dynamics and structure formation. Additionally, the Magellanic Nebula provides an exceptional laboratory for studying supernova remnants, SNRs. The diversity of these remnants, including core collapse and thermonuclear, offers a comprehensive view of how these explosive events impact their surroundings. Multi-wavelength observations spanning X-ray, optical, and radio frequencies reveal details of mechanisms, ejected material, supernova shocks on interstellar gas. Its rich population of planetary nebulae and asymptotic giant branch, AGB, stars provides crucial data on the late stages of stellar evolution. By studying how stars shed their outer layers, astronomers gain insight into the enrichment of the interstellar medium with heavy elements. Observations of dust production in AGB stars further enhance understanding of dust formation and recycling in galaxies, processes that influence both star formation and the cooling of interstellar gas. A focal point in stellar evolution research, this galactic neighbor provides an ideal in studying stars across a wide range of ages. Its well-resolved stellar populations offer key insights into how galaxies evolve over time. The presence of ancient stars acts as a fossil record of the early universe, allowing astronomers to reconstruct its chemical and dynamical history. Differences in metallicity and the central bar and outer regions further highlight the complexities of galactic evolution. The gravitational interplay between this system and its smaller companion, the Small Magellanic Cloud, SMC, remains a cornerstone of modern astrophysics. Their long-term rise to structures such as the Magellanic Bridge, a stream of stars and gas linking both galaxies, and the Magellanic Stream, a massive tail of gas trailing behind them. These formations provide an excellent laboratory for understanding tidal interactions, gas dynamics, and the stripping processes over cosmic timescales. Among its most active regions, the Tarantula Nebula stands out as a key site for studying the formation of massive stars. Hosting an exceptionally dense population of young stars and clusters, often compared to the intense star-forming environment of the universe. Observing this nebula allows astronomers to explore the conditions under which the first generations of stars formed and how their energetic feedback influenced surrounding matter. Within the nebula, R136 contains some of the most ever discovered, challenging theories of stellar evolution. And its stellar population, this Milky Way is a valuable resource for understanding the complex relationship between dust in galaxies. Its interstellar medium, rich in neutral hydrogen, molecular clouds, and ionized regions, is studied extensively across multiple wavelengths. These observations reveal intricate feedback mechanisms, where energy from stars regulates the cycling of gas and dust, shaping future star formation. The Magellanic System is pivotal in studying cosmic reionization, the epoch when the first galaxies ionized pervasive neutral hydrogen. Its low metallicity and active star formation make it a valuable proxy for early galactic conditions. By analyzing the ultraviolet radiation escaping from its star-forming regions, researchers gain insight into how the first galaxies contributed to reionize. Advances in spectroscopy have allowed astronomers to map its chemical enrichment history with increasing precision. Measurements of elements like magnesium and iron provide a timeline of nucleosynthesis events. These studies reveal multiple star-forming episodes punctuated by quiescent periods and bursts of renewed activity by external interactions. The chemical signatures of ancient stars also hint at the influence of different supernova types, including core collapse and type Ia explosions. The Magellanic Companion is further notable for its role in gravity-lensing. As one of the Milky Way's closest neighbors, it frequently aligns with background stars, creating opportunities to observe these rare phenomena. Microlensing events have been used to search for dark matter in the form of machos, massive compact halo objects, and to characterize exoplanets within the system. Findings from these studies have placed important constraints on dark matter's nature while expanding our knowledge of planetary systems in nearby galaxies. Additionally, this galactic neighbor plays a crucial role in understanding the dynamics of galaxy groups. Alongside the Small Magellanic Cloud, SMC, and the Milky Way, it forms a hierarchical system that exemplifies how galaxies evolve in a gravitationally bound environment. These define galaxy group dynamics, helping to interpret the large-scale structure of the universe. Beyond structural and stellar features, the Magellanic Cloud serves as a laboratory for investigating the life cycle of interstellar matter and the cosmic processes shaping galactic ecosystems. Its network of supernova remnants, SNRs, illuminates the violent deaths of massive stars while influencing their host galaxy. The relatively low extinction and minimal foreground interference make it an ideal target for multi-wavelength studies of these remnants. One of the most significant events, SN 1987A, provided an unprecedented real-time view of a supernova's evolution, from its initial outburst to the expanding debris field. The wealth of data from this explosion has driven decades of theoretical research into stellar death, neutron star formation, and black hole creation. Another critical area of study is the search for stellar streams, elongated structures of stars and gas formed through tidal interactions. The Magellanic Stream, a massive gaseous tail stretching hundreds of thousands of light-years, is one of the most prominent examples. Composed mainly of hydrogen, it represents both the LMC and SMC through gravitational encounters with each other, and the Milky Way. Understanding its structure and motion provides insight into the Milky Way's gravitational potential and dark matter distribution. High-resolution maps from radio telescopes such as Meerkat and ESCAP have revealed intricate substructures, shedding light on the complex forces shaping the stream. The Magellanic Galaxy's star-forming regions, particularly the Tarantula Nebula, offer unparalleled opportunities to study the birth of massive stars. While this nebula stream example, smaller regions throughout the galaxy provide additional insight into how different environments affect star formation. Variations across the system allow astronomers to explore how element abundance influences gas cloud collapse, protostar formation, and stellar feedback. These findings have been the early was the cosmic distances. This system remains a cornerstone. Its vast population of classical Cepheid variable stars has long been instrumental in refining the cosmic distance scale. The well-calibrated period relationship of these stars provides a fundamental rung on the cosmic distance ladder. With the Hubble Space Telescope and Gaia have this calibration, solidifying its role as a key benchmark for measuring the Hubble constant. However, ongoing discrepancies between different methods, known as the Hubble tension, persist, keeping the LMC at the forefront of efforts to resolve this cosmic puzzle. As one of visible galactic neighbors, the large Magellanic Cloud continues to captivate astronomers, offering a window into stellar evolution, galaxy interactions, and cosmology. Its proximity to the Milky Way enables detailed observations that would be impossible for more distant galaxies, making it an invaluable testbed for studying fundamental astrophysical processes. On a larger scale, LMC's eventual merger with the Milky Way presents a fascinating future for both galaxies. Simulations predict that this event, expected in about 2.5 billion years, will significantly reshape the Milky Way. Given its substantial mass, estimated at around 10% of our galaxies, the encounter could reorganize disk, trigger bursts of star formation, and create ripples in the stellar halo. This process will also redistribute dark matter, providing a natural experiment in galaxy assembly dynamics. The LMC's magnetic field adds another dimension to its Observations using polarized light-scale magnetic structuring the galaxy, influencing gas flows, motion, and cosmic ray propagation. Investigating these provides valuable origins and evolution still not good in astrophysics. Beyond professional research, the LMC is a source of inspiration for amateur astronomers and astrophotographers. Visible to the naked eye from the southern hemisphere, it has long been a cultural landmark, appearing in indigenous mythologies and aiding navigation. Through telescopes, its bright star clusters and nebulae showcase dynamic cosmic processes, connecting observers to the broader universe. From individual stars to intergalactic interactions, this galaxy remains central to astrophysical research. It bridges the local and the universal, offering a unique glimpse into the forces shaping the cosmos. Its relative proximity allows astronomers to examine processes that are otherwise challenging to observe in more distant systems. As one of the Milky Way's closest satellites, the LMC provides a window into the nature of smaller galaxies while contributing to broader cosmological studies. Its complexity spans diverse components: stellar populations, interstellar medium, dynamic interactions, and fundamental physical processes. Interstellar dust in the LMC plays a crucial role in the galaxy's life cycle. Dust grains, produced in the atmospheres of aging stars and supernovae, absorb and scatter light, re-emitting it in the infrared. Observations from the Spitzer Space Telescope and Herschel Space Observatory show notable differences in dust composition compared to the Milky Way, likely due to its lower metallicity. These variations affect star formation, as dust aids in cooling molecular clouds to temperatures suitable for stellar birth. The galaxy hosts a remarkable concentration of massive stars and stellar clusters. Several regions experience intense starburst activity, with conditions similar to those in the early universe. The Tarantula Nebula, for instance, contains thousands of massive stars, including some of the most luminous ever recorded. Their powerful stellar winds and short lifespans influence surrounding gas, enriching it with heavy elements through supernova explosions. These processes drive chemical evolution and regulate star formation. Beyond stellar evolution, the LMC plays an important role in gravitational wave research. Its numerous binary systems may include progenitors of neutron star or black hole mergers, events that produce detectable gravitation. Stories like LIGO and Virgo rely on these mergers to study extreme gravity and dense matter physics. Examining compact binary systems in this galaxy helps refine models of their formation and eventual coalescence, shedding light on the origins of gravitational wave signals. Another key area of study involves its gravifluence on the Milky Way's dark matter halo. The LMC's substantial mass disturbs the surrounding stellar halo, leaving observable imprints in the distribution of stars. Data from the Gaia Space Telescope, which provides high-precision measurements of stellar positions and motions, have been instrumental in tracking these disturbances. Modeling the interactions between the LMC and Milky Way is offering new insights into the shape, mass, and behavior of dark matter. The LMC also serves as a natural testbed for understanding galaxy formation. As a low-mass system, it offers out conditions in the early universe when small galaxies form larger structures. Of its evolution, combined with observations of its structure and composition, provide a framework for studying how galaxies grow over cosmic time. Its interactions with the Milky Way add another layer of highlighting how gravitational forces and environmental factors shape galactic studies. History, based on photometric and spectroscopic surveys, reveal a pattern of episodic activity. Periods of intense star formation alternate with quieter likely triggered by interactions with the Milky Way and SMC. These gravitational encounters compress gas reservoirs, inducing new star formation while simultaneously stripping material, contributing to structures like the Magellanic Stream. This cyclical process provides crucial data for understanding how galaxies evolve over billions of years. Ongoing and future missions will further expand our knowledge of this galaxy. Observations with the James Telescope, JWST, are expected to reveal new details about its star-forming regions, while radio arrays like ESCAP and Meerkat continue mapping the Magellanic Stream in unprecedented detail. Based facilities, including the extremely large telescope, will enhance studies of individual chemical compositions. By continuing to study the LMC, astronomers are uncovering fundamental insights into dark matter, stellar evolution, and galaxy interactions. Whether as a nearby laboratory for astrophysical phenomena or a glimpse past, this remarkable satellite remains essential for understanding the universe's history. LMC's status as an intermediate mass galaxy with low metallicity makes it a crucial laboratory for studying planetary systems and evolution. Lower metallicities are thought to influence planet formation, terrestrial planets, limiting the availability of heavy elements essential for their development. Detecting exoplanets in the LMC is challenging due to its distance, but in future missions, such as the Newman Space Telescope, discovery through providing valuable insights into planetary form such conditions. Another intriguing is the magnetic field observations. Magnetic fields play a fundamental role in shaping galaxies by influencing gas flows, star formation, and congregation. While the LMC's organize structures that trace spiral and tidal features. Investigating these magnetic properties could enhance our understanding of their origins and evolution across different galactic environments. With upcoming observatories set to expand our knowledge, the future of research is promising. The James Webb Space JWST, an unprecedented view of star formation regions, probing their structure and chemistry in detail. Meanwhile, the Square Kilometre Array, SKA, will map neutral hydrogen distribution, revealing gas dynamics and interactions. These efforts will complement data from Gaia, which continues to refine our understanding of stellar populations and kinematics in the LMC. The LMC remains central to astrophysics, offering a dynamic environment for studying galaxy of stellar physics and cosmic processes. Its history and unique properties provide a natural laboratory for exploring a broad range of phenomena, making it one of the most extensively examined extragalactic objects. Among the most compelling topics is its role in cosmic gas dynamics. The LMC contains vast reservoirs of neutral hydrogen, molecular gas, and ionized regions, essential for fueling star formation. Observations with ATCM have revealed intricate interstellar structures, including filaments, shells, and expanding bubbles, often linked to feedback from young stars and supernovae. Studying these features helps astronomers' energy transfer from stars regulate the formation of future generations. The LMC also provides key insights into galactic chemical evolution. Its relatively low metallicity reflects conditions in the early universe, offering a glimpse into the processes that shaped the first galaxies. Spectroscopic studies have mapped the abundance patterns of heavy elements produced in supernovae and lighter elements synthesized in AGB stars, refining models of nucleosynthesis and interstellar media medium enrichment. Another fascinating aspect is the LMC's population of pulsars and compact stellar remnants. Abundant supernova remnants serve as prime locations for neutron star and black hole discoveries. Pulsars, rapidly rotating neutron stars, act as precise cosmic clocks, helping probe interstellar medium properties, test general relativity, and study extreme matter physics. Binary pulsars within the LMC offer unique opportunities to explore accretion dynamics and interactions. The galaxy's stellar halo provides further clues about its formation history. Observations suggest that this diffuse structure contains relics of past mergers and accretion events, preserving a record of interstellar companions and the Milky Way. Analyzing the motions and compositions of halo stars enables astronomers to reconstruct the LMC's evolutionary timeline and gain insights into hierarchical galaxy assembly. In addition to its halo, the LMC's central bar and spiral-like features are key areas of interest. These structures likely result from internal dynamics and gravitational interactions with the Small Magellanic Cloud, SMC, and Milky Way. The central bar appears to host younger stellar populations compared to the outer regions, underscoring the complex relationship between galactic dynamics and star formation. High-resolution simulations, combined with data, are helping to unravel the processes that shape these features. As a satellite of the Milky Way, the LMC is also a crucial testbed for studying dark matter. Its surrounding dark matter halo influences its tidal interactions and overall stability. Comparing observational data with theoretical models allows researchers to constrain dark matter distribution and density, shedding light on this elusive component of the universe. The LMC's ongoing interaction with the Milky Way provides further opportunities to probe dark matter by studying gravitational perturbations and their effects on stellar motion. The LMC's variable stars have played a vital role in calibrating cosmic distances. Alongside Cepheid variables, it contains a large population of RR Lyrae stars, excellent standard candles for measuring extragalactic distances. These older, lower-mass pulsators provide complementary data for refining the cosmic distance ladder. Accurate measurements of the LMC's distance are essential for reducing uncertainties in key cosmological parameters, including the Hubble constant and the universe's age. As part of an ongoing gravitational interaction with the SMC and Milky Way, the LMC is actively shaping and being shaped by its surroundings. These interactions have produced spectacular structures such as the Magellanic Bridge, a stellar and gaseous link between the LMC and SMC, and the Magellanic Stream, an enormous gas trail extending across the southern sky. These features provide direct evidence of tidal forces at work, serving as a laboratory for studying material exchange between galaxies. Understanding these processes is fundamental to modeling hierarchical growth of galactic systems in the broader context of cosmic evolution. The future of research on the Large Magellanic Cloud, LMC, is set to be transformative with the next generation of astronomical observatories. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will map the galaxy in unprecedented detail, uncovering faint structures and transient phenomena previously beyond detection. The James Webb Space Telescope, JWST, will probe deep into its star-forming regions, revealing the birthplaces of stars and planets, while radio facilities like the Square Kilometre Array, SK, will provide unparalleled insights into its gas dynamics, interactions with the Milky Way, and role in the cosmic baryon cycle. With its rich tapestry of stars, gas, and dynamic interactions, the LMC continues to be a cornerstone in our understanding of galactic evolution. The study of its unique characteristics not only advances our knowledge of galaxy formation but also connects us to the broader history of cosmic development. Its proximity, combined with its distinct composition and history, makes it a natural laboratory for studying phenomena ranging from local to large-scale cosmic interactions. One particularly exciting avenue of research is its role in the creation and recycling of heavy elements. Active star-forming regions such as the Tarantula Nebula act as cosmic furnaces where nuclear reactions forge elements heavier than hydrogen and helium. These elements are subsequently dispersed into the interstellar medium through stellar winds and supernova explosions, enriching surrounding gas and fueling the formation of new stars and planets. Observing these processes in the LMC helps refine models of galactic chemical evolution, shedding light on how the universe evolved from its primordial state into the complex galaxies we see today. The LMC also serves as an important testbed for studying the life cycle of star clusters. Unlike the Milky Way, where dense dust obscures many clusters, its low foreground extinction allows for clear observations of stellar groupings at various evolutionary stages. This includes massive young clusters like R136, as well as older globular clusters that serve as a fossil record of past galactic activity. These observations help answer fundamental questions about how clusters form, evolve, and dissolve, as well as their influence on galactic structure. Another intriguing feature is its population of planetary nebulae, expanding shells of gas ejected by dying stars. These objects offer valuable insights into the late stages of stellar evolution, particularly for low and intermediate mass stars. By studying the shapes, compositions, and dynamics of planetary nebulae, astronomers gain a better understanding of how stars enrich their surroundings with elements like carbon and nitrogen. Additionally, the LMC's relatively low metallicity provides a unique opportunity to explore how a galaxy's chemical composition influences the behavior of planetary nebulae. The galaxy's rich collection of binaries and compact objects presents another avenue of profound interest. X-ray binaries, in which a neutron star or black hole accretes material from a companion, serve as natural laboratories for testing theories of accretion and relativistic jet formation. The recent detection of gravitational waves from black hole mergers has heightened interest in the LMC as a possible host for progenitor systems. By studying binary interactions within the galaxy, astronomers refine models of stellar evolution and compact object mergers, enhancing our understanding of gravitational wave events. On a larger scale, the LMC is crucial for understanding the assembly and evolution of the local group, which includes the Milky Way, Andromeda, and smaller satellite galaxies. Simulations of its motion suggest it may have been more massive in the past, potentially losing a significant portion of its material through interactions with the Milky Way. These findings have profound for our understanding of satellite evolution and the role of tidal forces in shaping galactic systems. One of its most visually striking features, the Magellanic Stream, remains an area of intense study. This massive trail of gas, stripped from the LMC in Small Magellanic Cloud, SMC, extends across a significant portion of the southern sky. It provides a remarkable opportunity to investigate tidal stripping, ram pressure, and material exchange between galaxies. Recent observations have detected not only hydrogen but also heavier elements, likely ejected through stellar feedback. Understanding the composition and motion of this stream instructing past interactions between the LMC, SMC, and the Milky Way. The LMC's ongoing interaction with the Milky Way also offers critical insights into galaxy mergers. As it orbits our galaxy, its gravitational influence distorts the Milky Way's stellar halo, creating ripples and streams that can be traced using Gaia data. These interactions are not only reshaping the LMC itself but also influencing the structure of the Milky Way. Simulations predict that their eventual merger will trigger a significant reorganization of the Milky Way's disk and halo, possibly igniting a burst of star formation. The LMC also plays a role in studying cosmic reionization, the era when the first galaxies ionized the intergalactic medium. Its active star-forming regions and low metallicity make it an ideal analog for early universe conditions. By examining how ultraviolet radiation escapes from its regions, astronomers gain insights into how the first galaxies contributed to reionizing the cosmos. These investigations, supported by observations from the Hubble Space Telescope and upcoming data from JWST, help bridge the gap between the distant past and the present. From the physics of stars to intergalactic interactions, the LMC continues to be an invaluable astrophysical resource. Its role as a benchmark for studying the cosmic baryon cycle, the continuous exchange of gas between galaxies and their surroundings, adds another dimension to its importance. Observations suggest it both accretes material from the Magellanic stream and loses gas through stellar feedback and tidal stripping. These processes are fundamental to sustaining star formation over billions of years and enriching the intergalactic medium with heavy elements. Stellar feedback processes in the LMC further highlight its significance. The Tarantula Nebula, the most active star-forming region in the local group, provides a vivid example of how massive stars shape their environment. Stellar winds, radiation pressure, and supernova explosions create large-scale structures such as bubbles and filaments, regulating gas flow and influencing future star formation. Studying these mechanisms refines theoretical models of galaxy evolution by showing how feedback influences gas retention and dispersal. The LMC is also a key environment for studying the full life cycle of stars. It hosts numerous protostars at various stages of development, offering a rare opportunity to observe stellar formation in detail. At the other end of the spectrum, its supernova remnants, neutron stars, and black holes provide insights into the most extreme astrophysical phenomena, from element synthesis to relativistic jet formation. Variable stars, including Cepheids, RR Lyrae stars, and long-period variables, further reinforce the LMC's value in cosmic distance measurements. Observations of Cepheids within the galaxy have helped refine the period-luminosity relationship, which underpins the cosmic distance ladder. These advancements certainties in Hubble constant calculations, though ongoing discrepancies between measurement methods highlight the need for further study. Its interactions with the SMC and Milky Way have also produced complex tidal structures like the Magellanic Bridge and Magellanic Stream, which serve as natural laboratories for studying gas dynamics and galaxy evolution. Meerkat and ESCAP radio telescopes have revealed intricate details of these structures, improving our understanding of material transfer between galaxies. Magnetic fields in the LMC represent another area of growing interest. Polarization studies show a coherent magnetic structure that follows its spiral and tidal features. These fields influence charged particle behavior, flow, and cosmic ray propagation, making their study essential for understanding magnetism's role in galaxy formation. As technology advances, the LMC will continue to be an essential reference point for astrophysics. With upcoming surveys, space missions, and high-resolution simulations, it remains at the heart of efforts to decipher the fundamental forces shaping galaxies, stars, and the cosmos itself. On a cosmological scale, the Large Magellanic Cloud contributes significantly to our understanding of hierarchical galaxy growth. Simulations suggest it may have once belonged to a larger group of galaxies before being captured by the Milky Way. This scenario provides valuable insights into the processes of galactic assembly and evolution within the framework of large-scale cosmic structures. Its eventual merger with the Milky Way, expected in several billion years, is predicted to reshape both galaxies, triggering bursts of star formation and redistributing dark matter within their halos. Another compelling area of study involves the potential presence of exoplanets. While detecting planetary systems within this neighboring galaxy is challenging due to its distance, microlensing surveys have identified promising candidates. These discoveries offer a glimpse into planetary formation in different galactic environments, revealing how factors like metallicity influence the process. Future missions, such as the Nancy Grace Roman Space Telescope, are expected to enhance our ability to detect and analyze exoplanets beyond the Milky Way. The Magellanic Galaxy is also a crucial laboratory for fundamental physics. Its rich population of pulsars and binary systems serves as a natural testing ground for gravitational theories and the behavior of matter under extreme conditions. Observations of these objects have been used to test Einstein's general relativity, study the equation of state for neutron stars, and investigate the formation of compact stellar remnants. The next generation of observatories promises to unlock even more secrets about this galactic neighbor. The Vera C. Rubin Observatory will conduct deep surveys, mapping faint stellar populations, tidal structures, and transient phenomena with unprecedented precision. The James Webb Space Telescope, JWST, will reveal the intricacies of its star-forming regions and interstellar medium at resolutions previously unattainable. Meanwhile, the Square Kilometre Array, SKA, will provide detailed hydrogen maps, shedding light on the gas dynamics and interactions shaping the galaxy's evolution. The Great Magellanic Cloud remains a cornerstone of modern astrophysics, bridging the local universe with the distant past. Its study advances our understanding of galactic dynamics and the broader history of cosmic evolution. As one of the Milky Way's most prominent satellite galaxies, it plays a vital role in unraveling the complex interactions between galaxies of years. One of its features is its vibrant star-forming regions, most notably the Tarantula Nebula. This colossal nebula, the most active stellar nursery in the local group, produces massive stars at an extraordinary rate. The intense ultraviolet radiation from these young, hot stars ionizes the surrounding gas, shaping intricate structures within the interstellar medium. Energy feedback from massive stars influences star formation across the region and enriches surrounding gas with heavy elements. The Magellanic Stellar Cloud provides a unique environment for studying stellar evolution across various masses and life stages. Its population of Wolf-Rayet stars, red supergiants, and other massive objects offers valuable insights into how stars evolve and end their lives, whether as supernovae, neutron stars, or black holes. Its lower metallicity further makes it a compelling analog for the conditions of the early universe, where similar environments were more common. A critical component of the Magellanic Nebular Galaxy is its population of variable stars. Classical Cepheids, RR Lyrae stars, and other pulsating objects within this galaxy have played a crucial role in calibrating the cosmic distance scale. These stars function as standard candles, enabling astronomers to refine distance measurements with exceptional accuracy. Pinpointing its exact distance is key to reducing uncertainties in the Hubble constant, further refining our understanding of the universe's expansion. The Magellanic Companion is also a valuable subject for studying interstellar gas dynamics. Its vast reservoirs of neutral hydrogen and molecular clouds provide a detailed picture of how gas moves and cycles through a galaxy. Observations have revealed the interplay between internal processes, such as stellar feedback, and external influences like tidal interactions with the Milky Way and Small Magellanic Cloud. These findings enhance our knowledge of how gas is recycled and redistributed, fueling star formation and galactic evolution. Its dark matter halo is another focus of intense study. The rotation curve of the Magellanic Galactic Companion suggests it is embedded in a substantial halo of dark matter, whose distribution and density remain key research areas. Modeling the gravitational effects between this galaxy, the Milky Way, and the SMC provides critical data on dark matter's role in shaping galactic structures. The Magellanic Cosmic Cluster also offers a real-time view of galaxy interactions. Tidal forces between this system, the SMC, and the Milky Way have created dramatic structures such as the Magellanic Stream, a massive tail of neutral hydrogen stretching across the southern sky. These features preserve the history of interactions between these galaxies, providing an observational record of material exchange and environmental effects. Understanding their formation helps reconstruct the sequence of events that shape the present-day Magellanic Dwarf Galaxy and similar systems in the universe. With its irregular shape and dynamic history, this satellite remains one of the most valuable objects for studying small galaxies and their role in the cosmic ecosystem. Its position in the local group, coupled with active star formation and interactions with larger galaxies, makes it a prime laboratory for understanding the life cycles of galaxies and stars. Observations of this evolving system will continue to refine our knowledge of galactic mergers, interstellar matter cycles, and fundamental astrophysical processes. The Magellanic Dwarf Galaxy remains an essential piece of the puzzle in understanding how galaxies grow, interact, and transform across cosmic time. A fascinating feature of this southern stellar companion is its diverse population of star clusters. These include ancient globular clusters, remnants of the galaxy's early history, as well as younger open clusters that capture snapshots of ongoing star formation. By analyzing these stellar groupings, astronomers can trace the evolution of this system, uncovering how it has grown through interactions with its cosmic surroundings. Such clusters provide critical clues about the conditions under which stars and planets formed in the early universe, preserving ancient metallicities and dynamical patterns. The Magellanic Star Factory also hosts the Tarantula Nebula, the most active star-forming region in the local group. This vast stellar nursery contains the R136 cluster, home to some of the most massive and luminous stars ever discovered. Intense radiation and stellar winds from these giants sculpt surrounding gas clouds, carving intricate cavities in the interstellar medium. Studying these processes offers a rare opportunity to observe stellar feedback in action, refining models of starburst galaxies across cosmic history. This cosmic companion is also a prime site for exploring galactic gas flows. It contains one of the richest reservoirs of neutral hydrogen in the local group, with radio surveys revealing filaments, bubbles, and tidal structures shaped by gravitational interactions. Encounters with the Small Magellanic Cloud, SMC, and the Milky Way have stripped gas from its outer regions, forming the Magellanic Stream and Bridge. These tidal structures serve as an invaluable laboratory for understanding how galaxies exchange material and how gravitational forces influence their evolution. Another striking aspect of this starburst galaxy is its distinctive stellar population. With lower metallicity than the Milky Way, it provides an analog in early galaxies, offering insights into stellar nucleosynthesis under primordial conditions. The chemical enrichment of the interstellar medium by supernovae within this system enhances our understanding of how galaxies evolve and seed the cosmos with heavier elements. The system is also a crucial natural laboratory for studying dark matter. Simulations indicate that its dark matter halo extends well beyond the visible galaxy, influencing its motion and interactions. Tracking the movements of stars and gas under gravitational influence offers direct evidence of the halo's mass and structure. Furthermore, its eventual merger with the Milky Way will provide real-world insights into how galaxies grow by accreting smaller companions, a process fundamental to cosmic evolution. The Great Southern Nebular Cloud, as it is sometimes poetically called, is home to a wide array of compact objects, including neutron stars and black holes. These remnants of stellar collapse provide an excellent testing ground for extreme physics. Observations of X-ray binaries and pulsars within this galaxy help astrophysicists probe the mechanics of accretion disks, relativistic jets, and neutron star interiors, offering key insights into the fundamental laws of matter and gravity. Additionally, this galactic companion plays a crucial role in the overall dynamics of the local group. Its gravitational interactions with the Milky Way and SMC have significantly influenced the structure of all three galaxies, producing tidal streams, bridges, and extended stellar tails. Mapping these structures with instruments like Gaia and next-generation radio surveys enables astronomers to reconstruct the past orbits of these systems, revealing a complex history of interactions spanning billions of years. This extraordinary galactic system, regardless of the name given to it, continues to provide transformative insights into the processes that shape galaxies, stars, and the wider universe. The intergalactic jewel of the South, often referred to as the Large Magellanic Cloud, LMC, occupies a unique position between dwarf galaxies and larger spirals, making it an essential subject for studying galactic evolution, star formation, and cosmic interactions. This remarkable system holds key information about processes that have shaped galaxies throughout the history of the universe. The Southern Stellar Nursery is widely recognized for its prolific star-forming regions, particularly the Tarantula Nebula. This stellar factory mirrors conditions in the early universe, where galaxies underwent intense star formation. Within this nebula, astronomers study how molecular clouds collapse into stars, how radiation and stellar winds sculpt their environments, and how supernovae recycle material back into the interstellar medium. At the same time, the sky's star forge holds a deep record of ancient history, preserving some of the oldest globular clusters in the local group. These stellar fossils provide invaluable data about the universe as it was billions of years ago. Examining their metallicities and kinematics helps astronomers uncover the mechanisms of early galaxy formation and the role of mergers in assembling today's larger systems. The Magellanic Star Arc further acts as a dynamic laboratory for understanding galaxy interactions. Its gravitational interplay with the SMC and Milky Way has led to the creation of striking tidal features such as the Magellanic Stream and Bridge. These formations serve as observational proof of how gas and stars are exchanged between galaxies, fueling new bursts of star formation and reshaping galactic ecosystems. The stellar labyrinth of this neighboring galaxy is especially valuable for examining low metallicity environments. Lacking many of the heavier elements common in the Milky Way, it presents a rare opportunity to observe star formation and evolution under conditions that mimic those in the early universe. The chemistry and dynamics of these stars contribute to refining our models of nucleosynthesis and galactic chemical enrichment. The Southern Star Canyon, as some astronomers affectionately call it, is a treasure trove of compact objects. Its abundant supernova remnants, binary systems, and neutron stars allow researchers to explore the physics of extreme environments. Across multiple wavelengths, X-ray, radio, and optical, these objects provide critical data on gravitational interactions, accretion processes, and relativistic phenomena. The Magellanic Cosmic Reservoir contains vast supplies of neutral hydrogen gas, fueling future generations of stars. Detailed radio surveys track how this gas flows through the galaxy, condenses into molecular clouds, and eventually ignites star formation. These observations also reveal interactions between its gas reservoirs and the Milky Way's halo, shedding light on the broader galactic ecosystem. As an irregular marvel, this galaxy offers a compelling study of morphology's impact on galactic evolution. Unlike well-structured spirals, its irregular shape reflects a turbulent past shaped by both internal forces and external tidal effects. These distortions offer a natural experiment in how galaxies evolve under the influence of gravitational encounters and stellar feedback. The sky's ancient traveler is a key subject in the study of dark matter. The motions of stars and gas reveal the gravitational effects of its extended dark matter halo, which stretches far beyond its visible boundaries. Modeling these dynamics helps researchers constrain the nature and distribution of dark matter, contributing to one of modern physics' most pressing mysteries. Finally, the Southern Celestial Workshop remains a dynamic part of the local group, continually interacting with its neighbors. The tidal forces it experiences are not only reshaping its own structure but also leaving lasting imprints on the Milky Way's stellar halo. These ongoing interactions provide a glimpse into the future of the local group and the eventual fates of its member galaxies. As one of the most thoroughly studied extragalactic systems, this southern gem continues to provide new revelations about galaxy formation, stellar evolution, and the intricate web of cosmic interactions shaping the universe. The Southern Celestial Dynamo, widely recognized as the Large Magellanic Cloud, functions as a cosmic engine driving our understanding of galaxy dynamics, star formation, and interstellar interactions. With its irregular yet structured form, this remarkable system offers insight into processes that shape the cosmos, from molecular cloud collapse to large-scale intergalactic flows. The Magellanic Stellar Forge serves as a hub for stellar production, housing the Tarantula Nebula, an exceptionally active star-forming region. This vast nursery provides a real-time model of how massive molecular clouds collapse to form clusters, with stellar feedback, winds and radiation from young, hot stars, sculpting surrounding gas into intricate structures. The Southern Galactic Cradle preserves both infant stars and ancient relics, making it an ideal site for studying stellar evolution. Ancient globular clusters act as benchmarks for understanding the early universe, while massive young clusters reveal dynamic processes shaping modern galaxies. By analyzing these populations together, astronomers uncover a narrative spanning billions of years. The intergalactic alchemy engine reflects the role of this galaxy in chemical evolution. Its lower metallicity mirrors conditions in the early universe, allowing researchers to study the production and dispersal of elements heavier than helium, such as carbon, oxygen, and iron. Supernovae within this system serve as cosmic alchemists, enriching the interstellar medium and laying the foundation for future stellar and planetary formation. The cosmic tidal sculpture illustrates the profound gravitational interactions it experiences with the Milky Way and small Magellanic Cloud. These forces create vast tidal structures like the Magellanic Bridge and Stream, tracing the exchange of gas between galaxies and shaping their evolution. These features provide a unique laboratory for studying how gravitational forces influence star formation and galactic structure. The sky's hydrogen reservoir highlights the vast stores of neutral hydrogen fueling new generations of stars. Radio observations have mapped intricate filaments and voids within this gas, shaped by stellar feedback and gravitational encounters. These findings enhance our understanding of how gas flows sustain star formation across cosmic time. The southern cosmic clockwork reflects the precise and predictable motions of stars and gas. Mapping its rotation curve reveals the presence of an extensive dark matter halo, a hidden framework governing its dynamics. This provides a valuable testing ground for theories on dark matter's influence in galactic evolution. The Magellanic starburst nexus showcases regions of intense stellar feedback, where supernova explosions and powerful winds inject energy into surrounding gas, creating vast cavities and triggering secondary waves of star formation. These processes play a critical role in regulating the galaxy's long-term ability to sustain stellar birth. The celestial collision zone foreshadows an eventual merger with the Milky Way. Over billions of years, it will spiral closer, undergoing tidal disruption and contributing its stars, gas, and dark matter to its larger neighbor. This event mirrors countless mergers that have shaped galaxies across the universe, offering a glimpse into the future of galactic evolution. The dynamo of change also serves as a key reference for understanding magnetic fields in galaxies. Polarization studies reveal large-scale magnetism threading through its interstellar medium, influencing gas movement and possibly playing a role in star formation. These insights contribute to our broader understanding of magnetism's role in shaping cosmic structures. The Southern Star River represents the ongoing flow of stars and gas between this galaxy, and the Milky Way. Stretching across hundreds of thousands of light-years, this dynamic feature records past interactions and future trajectories, captured in detail by radio and optical surveys. The stellar time capsule preserves remnants of past events through its rich populations of variable stars, supernova remnants, and compact objects like neutron stars and black holes. These stellar fossils provide astronomers with crucial tools for reconstructing its history, tracing cycles of formation, destruction, and renewal. Each perspective, whether as a star factory, a cosmic sculptor, or a dark matter laboratory, highlights its importance in unraveling the mysteries of the universe. The Large Magellanic Cloud, in all its complexity, stands as one of the most invaluable natural laboratories in astrophysics. It is not just a satellite of the Milky Way but a dynamic system encapsulating the processes that shape galaxies over billions of years. Its significance extends far beyond the local group, influencing our understanding of galactic evolution and the larger-scale structure of the cosmos. At the core of its importance is its ability to link the local and distant universe. By studying its star-forming regions, interstellar medium, and stellar populations, astronomers reconstruct conditions that shaped galaxies in the early epochs of cosmic history. Its low metallicity offers a rare glimpse into environments that parallel the young universe, providing crucial data for understanding how the first galaxies formed, evolved, and enriched their surroundings. Its interactions with the SMC and Milky Way reveal the complexities of galactic motion and material exchange. These gravitational encounters shape the structures of all three galaxies, driving the flow of gas and stars that sustain their evolution. Tidal features like the Magellanic Stream and Bridge serve as records of these forces, offering a direct observational link to processes that take billions of years to unfold. Beyond galaxy evolution, this system provides an unparalleled environment for studying the life cycles of stars. From the massive, luminous inhabitants of the Tarantula Nebula to ancient globular clusters and compact remnants, it contains examples of every stage of stellar evolution. Its variable stars, such as Cepheids and RR Lyrae, remain fundamental to refining the cosmic distance scale, anchoring our measurements of the universe's expansion. These contributions are essential in addressing key cosmological questions, including ongoing debates over the Hubble constant. The rich interstellar medium, composed of molecular clouds, neutral hydrogen, and ionized gas, supplies the raw material for star formation. Observations reveal how galaxies regulate this process through feedback mechanisms, where energy from massive stars and supernovae shapes the interstellar medium. These interactions are critical to understanding how galaxies sustain star formation over time and how they contribute to the chemical enrichment of intergalactic space. By continuously shaping our understanding of the universe, this southern gem remains at the forefront of astrophysical research, offering endless opportunities to study the mechanisms that govern galaxies, stars, and cosmic evolution. Moreover, this neighboring galaxy plays a crucial role in dark matter research. Its rotational dynamics and tidal interactions with the Milky Way offer direct evidence of dark matter's influence on galaxy evolution. By analyzing its distribution within both the visible structure and its surrounding halo, researchers gain deeper insights into this elusive substance, which dominates cosmic mass yet remains undetectable through conventional methods. Looking ahead, this dynamic system will remain a cornerstone of astrophysical research for decades. Upcoming observatories promise to reveal even more of its mysteries. The James Webb Space Telescope will explore its star-forming regions and interstellar dust with unprecedented precision, while the Vera C. Rubin Observatory will map its stellar populations and tidal features in remarkable detail. Additionally, the Square Kilometre Array will refine our understanding of its neutral hydrogen content and its ongoing interactions with the Milky Way. Perhaps one of the most compelling aspects of this galactic neighbor is its future. In approximately 2.5 billion years, it will merge with the Milky Way, triggering transformative events that will reshape both galaxies. This impending collision provides a real-time example of hierarchical galactic growth, illustrating how stars, gas, and dark matter redistribute over cosmic timescales, processes that have sculpted galaxies throughout history. Beyond its scientific importance, this celestial landmark has also held a deep cultural significance. Visible to the naked eye from the southern hemisphere, it has inspired myths, navigational practices, and astronomical observations for millennia. Today, it continues to captivate astronomers, acting as a bridge between our local universe and the vastness beyond. In the end, this satellite galaxy is far more than a companion to the Milky Way. It is a dynamic and evolving system that encapsulates the complexity of the cosmos. From its star clusters and gas flows to its gravitational interactions and dark matter halo, it tells a story of cycles, transformation, and growth. As research continues, it not only expands our knowledge of the universe but also reinforces the interconnected nature of cosmic evolution, an enduring testament to the grandeur of the cosmos. The quasar that changed the universe, 3C273. The universe is vast, ancient, and full of extraordinary phenomena. Among the most luminous and enigmatic of these are quasars, celestial objects so bright that they outshine entire galaxies. The discovery of quasars marked a turning point in our understanding of the cosmos, revealing a universe far more dynamic and diverse than previously imagined. At the heart of this revelation was 3C273, the first quasar to be identified and studied in detail. Its discovery in 1963 by astronomer Martin Schmidt fundamentally reshaped the field of astrophysics and provided a new lens through which to view the cosmos. This is the story of 3C273, the quasar that changed everything. It is a story of discovery, innovation, and the relentless human pursuit of knowledge. From its origins as a mysterious radio source to its current role as a cornerstone of modern astronomy, 3C273 continues to illuminate the mysteries of the universe and inspire new generations of scientists and dreamers. The mystery of 3C273. In the early 1960s, the universe appeared relatively tame to astronomers. Stars, galaxies, and nebulae filled the observable cosmos, and while phenomena like supernovae and pulsars hinted at its complexity, the true scale of its dynamism was not yet understood. The field of radio astronomy was still in its infancy, but it was already revealing strange and unexpected sources of radio waves, many of which did not correspond to any known celestial objects. Among these was an unassuming radio source catalogued as 3C273 in the third Cambridge Catalogue of Radio Sources. Located in the constellation Virgo, 3C273 appeared to emit a faint but consistent signal in the radio spectrum. When optical astronomers pointed their telescopes at its location, they found a star-like object that defied easy classification. Its brightness suggested it was a relatively close object, perhaps a peculiar star, but its behavior and characteristics hinted at something far stranger. The breakthrough came when Martin Schmidt, a Dutch-American astronomer at the Palomar Observatory, analyzed the optical spectrum of 3C273. Using the 200-inch Hale telescope, Schmidt identified unusual spectral lines in the object's light. These lines were shifted toward longer wavelengths, a phenomenon known as redshift. Redshift occurs when light waves are stretched as an object moves away from the observer, similar to the way a sound lowers in pitch as a train recedes into the distance. The degree of redshift in 3C3 was extraordinary, indicating that the object was receding from Earth at an incredible speed. This redshift placed 3C273 at a distance of over 2 billion light-years, far beyond the boundaries of the Milky Way. What made this discovery even more astounding was the object's luminosity. Despite its immense distance, 3C273 shone with a brightness equivalent to 4 trillion suns, outshining entire galaxies. It was not a star but something entirely new, a quasar, or quasi-stellar object, powered by processes more energetic than anything previously observed. What is a quasar? Quasar galaxies powered by supermassive black holes. These black holes, millions to billions of times the mass of the Sun, are surrounded by disks of gas and dust known as accretion disks. As matter spirals into the black hole, it is heated to extreme temperatures by friction and gravitational forces, releasing immense amounts of energy in the form of electromagnetic radiation. This process, known as accretion, is among the most efficient mechanisms for converting mass into energy, making quasars some of the brightest objects in the universe. 3C273 became the prototype for studying these enigmatic objects. Its relatively close proximity allowed astronomers to investigate its properties in detail, providing critical insights into the nature of quasars and the extreme environments near supermassive black holes. The discovery of 3C273 also demonstrated that the universe was far more active and diverse than previously believed, with processes occurring on scales of energy and time that defied conventional understanding. The unique features of 3C273. Located approximately 2.4 billion light-years away in the constellation Virgo, 3C273 remains one of the most studied quasars in the universe. Its luminosity is roughly 4 trillion times that of the Sun, making it visible even with modest telescopes. Unlike most quasars, which are too distant to be observed with amateur equipment, 3C273 is a favorite target for astronomy enthusiasts, who can glimpse this cosmic powerhouse with relative ease. One of the most intriguing features of 3C273 is its variability. The quasar's brightness changes over weeks or months, reflecting the turbulent processes occurring in its accretion disk. These fluctuations provide valuable clues about the size, structure, and behavior of the disk, offering a rare glimpse into the dynamics of matter spiraling toward a supermassive black hole. Another remarkable aspect of 3C273 is its jets. These are streams of high-energy particles ejected from the poles at nearly the speed of light. The jets, which extend for hundreds of thousands of light-years, are among the most studied phenomena in astrophysics. They provide critical insights into the magnetic fields and relativistic processes near black holes, as well as the impact of quasars on their surrounding environments. Why 3C273 matters. The discovery of 3C273 was a turning point in astronomy. It proved that the universe was not a static, unchanging place but a dynamic and evolving system filled with extreme phenomena. Quasars like 3C273 revealed the existence of supermassive black holes and the energetic processes that occur in their vicinity, fundamentally altering our understanding of galaxies and their evolution. Moreover, 3C273 provided a new tool for exploring the universe. Because of their immense brightness and redshift, quasars can be used to study the conditions in the early universe. Their light, which travels for billions of years to reach us, carries information about the intergalactic medium and the large-scale structure of the cosmos. By analyzing the spectra of quasars, astronomers can map the distribution of matter, study the evolution of galaxies, and probe the mysteries of dark matter and dark energy. The ongoing study of 3C273. Even decades after its discovery, 3C273 remains a focal point for research. Advances in technology, from space-based observatories to computer simulations, have allowed scientists to investigate the quasar in unprecedented detail. Observations across multiple wavelengths, from radio to gamma rays, continue to reveal new aspects of its behavior and structure, while theoretical models refine our understanding of the processes driving its luminosity. As new telescopes like the James Webb Space Telescope and the Square Kilometre Array come online, the study of 373 is poised to enter a new era. These instruments will provide deeper insights into the physics of quasars, the environments of supermassive black holes, and the role of quasars in shaping the universe. The text is already expanded significantly, but to reach approximately 100,000 characters, I can continue adding detailed sections about 3C273's implications for cosmology, its role in inspiring technological advancements, its cultural and philosophical impact, and the future of quasar research. Let me know if you'd like me to proceed with additional expansion. The broader implications of 3C273. The discovery of 3C273 opened the door to a deeper understanding of the universe's scale and structure. Beyond its immediate significance in identifying quasars, 3C273 has served as a gateway to exploring fundamental questions about the universe's composition, evolution, and future. Its light, which began its journey billions of years ago, offers a direct connection to the early universe, providing astronomers with a unique tool to probe its mysteries. Quasars as probes of the early universe. Because the light from 3C273 has traveled for over 2 billion years, it carries with it information about the intergalactic medium it passed through on its way to Earth. This medium, consisting of gas, dust, and dark matter, holds critical clues about the universe's structure and evolution. By analyzing how the quasar's light interacts with this material, astronomers can reconstruct a detailed picture of the cosmos at various points in its history. Quasars are particularly valuable for studying the epoch of reionization, a critical period in the early universe when the first stars and galaxies formed, re-illuminating the cosmos after the Dark Ages. During this time, ultraviolet light from young stars and quasars ionize the surrounding hydrogen gas, transforming the universe into the transparent state we observe today. The light from 3C273 provides indirect evidence of this process, helping researchers understand how the first structures in the universe emerged and evolved. The role of 3C273 in mapping the cosmic web. The large-scale structure of the universe, often described as the cosmic web, consists of vast filaments of matter connecting galaxies and clusters across enormous distances. This structure is shaped by the gravitational influence of dark matter, which acts as the scaffolding for galaxy formation. The light from quasars like 3C200 passes through these filaments, absorbing and re-emitting radiation in ways that reveal their composition and distribution. By studying these interactions, astronomers can map the cosmic web with incredible precision. This work has profound implications for understanding the distribution of both visible and dark matter in the universe. It also provides insights into the role of gravity, dark energy, and other forces in shaping the cosmos. Technological advancements driven by 3C. The discovery and study of 3C273 have driven significant advancements in astronomical instrumentation and techniques. From the development of high-resolution spectrographs to the refinement of interferometry, the need to understand quasars has spurred innovation across multiple fields. These technologies, in turn, have found applications far beyond astronomy, influencing areas such as telecommunications, medical imaging, and even artificial intelligence. Interferometry and high-resolution imaging. One of the most significant technological breakthroughs inspired by 3C273 is the develometry. This technique combines signals from multiple telescopes to create a single high-resolution image, allowing astronomers to study fine details in distant objects. Interferometry has been instrumental in observing the jets of 3C273, revealing their structure and behavior on scales as small as a few light-years. The success of interferometry in studying 3C273 paved the way for projects like the Event Horizon Telescope, which produced the first-ever image of a black hole in 2019. These achievements demonstrate the ripple effects of scientific curiosity, as the tools developed for one purpose lead to breakthroughs in entirely new areas. Multi-wavelength astronomy. The study of 3C273 also highlighted the importance of observing celestial objects across the entire electromagnetic spectrum. Quasars emit radiation in every wavelength, from radio waves to gamma rays, and each part of the spectrum provides unique information about their properties. This realization led to the construction of specialized telescopes and observatories capable of detecting multiple wavelengths, such as the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope. These instruments have expanded our understanding of 3C273 and other quasars, revealing the high-energy processes that power their immense luminosity. Cultural and philosophical impact of 3C273. Beyond its scientific contributions, 3C273 has had a profound impact on culture and philosophy. Its discovery challenged humanity's understanding of our place in the cosmos, expanding our perception of time, distance, and scale. The realization that such an energetic and distant object could exist forced us to confront the vastness of the universe and our own relative insignificance within it. A humbling perspective. The light from 3C273 began its journey over years ago, long before Earth had developed complex life. This temporal distance reminds us that we are part of a much larger story, one that began long before us and will continue long after we are gone. For many, this perspective is both humbling and inspiring, emphasizing the interconnectedness of all things and the enduring power of the universe to surprise and challenge us. Inspiring generations of scientists and dreamers. The discovery of 3C273 has inspired countless individuals to pursue careers in science, technology, and exploration. Its story, marked by curiosity and perseverance, serves as a reminder that even the most puzzling phenomena can be understood through careful observation and analysis. Educational programs and public outreach efforts frequently highlight 3C273 as an example of how science can unlock the mysteries of the universe, encouraging students and enthusiasts to look to the skies with wonder and determination. The future of quasar research. As astronomy enters a new era of discovery, 3C273 will continue to play a central role in advancing our understanding of the universe. Upcoming projects like the Vera C. Rubin Observatory, the European Extremely Large Telescope (ELT), and the Square Kilometre Array (SKA), promise to revolutionize the study of quasars, providing unprecedented levels of detail and sensitivity. Next-generation observatories. The Vera C. Rubin Observatory, set to begin operations in the coming years, will conduct a 10-year survey of the sky, capturing detailed images of millions of quasars, including 3C273. This data will allow astronomers to study the variability of quasars over time, providing new insights into the dynamics of accretion disks and the growth of supermassive black holes. The European Extremely Large Telescope (ELT) will offer unparalleled resolution, enabling scientists to study the fine details of 3C273's jets, accretion disk, and surrounding environment. These observations will help refine our understanding of the processes that drive quasars and their impact on their host galaxies. Expanding the boundaries of knowledge. As we continue to study 3C273, we will undoubtedly uncover new mysteries and challenges, pushing the boundaries of what we know about the universe. Each discovery will build on the foundation laid by Martin Schmidt and his contemporaries, ensuring that the legacy of 3C273 endures for generations to come. Conclusion: the eternal light of 3C273. The journey of 3C273 is far from over. Its light, which has traveled for billions of years, continues to illuminate the path to discovery, guiding us toward a deeper understanding of the universe and our place within it. From its humble origins as a puzzling radio source to its current role as a cornerstone of astrophysical research, 3C273 embodies the spirit of exploration and the power of science to reveal the unknown. As humanity gazes at the stars and ventures into the cosmos, 3C273 will remain a symbol of curiosity, innovation, and the boundless potential of discovery. Its brilliance, shining across space and time, is a reminder that the universe is vast, mysterious, and full of wonders yet to be uncovered. The unfolding legacy of 3C273. The legacy of 3C273 is a testament to how one discovery can spark an entire revolution in science, opening new avenues of exploration and inquiry. While much has been learned since Martin Schmidt's initial analysis in 1963, 3C273 remains at the forefront of astrophysical research, continuing to challenge our understanding of the universe and inspire new generations of scientists. The multidisciplinary impact of 3C273. The discovery of 3C273 was not just a milestone in astronomy but a multidisciplinary achievement that continues to influence fields ranging from theoretical physics to engineering and beyond. The technologies developed to study quasars have found applications in numerous areas of science and industry. Advancing spectroscopy. The analysis of 3C273's redshift required advanced spectroscopic techniques that have since been refined and expanded. Modern spectrographs, capable of analyzing light across the entire electromagnetic spectrum, have been used not only to study celestial objects but also to detect chemical compositions in fields like environmental science, materials engineering, and planetary exploration. For instance, the spectroscopic methods pioneered in studying quasars now enable astronomers to analyze the atmospheres of exoplanets. By observing how light interacts with the gases surrounding distant worlds, scientists can search for biomarkers, chemical signatures that may indicate the presence of life. The technology that helped decode the mysteries of 3C273 could one day lead to the discovery of extraterrestrial life. Driving computational innovation. The study of 3C273 also fueled advancements in data analysis and computational methods. The complexity of quasar light curves, variability, and spectral data required new algorithms to model and interpret. These computational tools have since evolved into machine learning and artificial intelligence, AI, systems that are now applied across a wide range of fields. AI-driven analysis of quasar data enables astronomers to identify patterns and relationships that would be impossible to detect manually. These systems are increasingly being used to analyze the vast datasets generated by modern telescopes, allowing scientists to uncover subtle phenomena and make connections between seemingly unrelated observations. Quasars and the evolution of galaxies. One of the most profound contributions of 3C273 to astrophysics is its role in understanding the evolution of galaxies. Quasars are now recognized as a key phase in the life cycle of galaxies, representing periods of intense activity when supermassive black holes consume large amounts of matter. This process releases enormous amounts of energy, which can have dramatic effects on the surrounding galaxy. Feedback mechanisms. The energy emitted by quasars, particularly in the form of jets and outflows, can heat and expel gas from the galaxy, suppressing star formation. This process, known as feedback, plays a crucial role in regulating the growth of galaxies and maintaining the balance between star formation and black hole activity. Observations of 3C273 have provided valuable insights into these feedback mechanisms, showing how the quasar's jets interact with the surrounding gas and influence the evolution of its host galaxy. These studies have helped refine models of galaxy formation and growth, shedding light on the complex interplay between matter, energy, and gravity on cosmic scales. Tracing cosmic history. By studying quasars like 3C273, astronomers can also trace the history of black hole formation and growth. The supermassive black hole at the center of 3C273 likely formed through the merger of smaller black holes and the accretion of matter over billions of years. Understanding this process provides a window into the early stages of galaxy formation and the conditions that allowed black holes to grow to such immense sizes. A tool for cosmic cartography. Quasars are not just objects of interest in their own right, they are also invaluable tools for mapping the universe. The light from 3C273 and other quasars acts as a beacon, illuminating the intervening space and revealing the structure of the cosmos on the largest scales. Gravitational lensing. One of the most fascinating phenomena associated with quasars is gravitational lensing. When the light from a distant quasar passes near a massive object, such as a galaxy cluster, the gravitational field of the intervening object bends and magnifies the light. This effect creates multiple images of the quasar or distorts its appearance, providing astronomers with a natural, magnifying glass to study the universe. Gravitational lensing has been used to study the distribution of dark matter, the mysterious substance that makes up most of the universe's mass but does not emit or absorb light. Quasars like 3C273 have played a key role in these studies, helping scientists map the invisible scaffolding of the cosmos. Probing the intergalactic medium. As the light from 3C273 travels across billions of light-years, it passes through vast clouds of intergalactic gas. This gas imprints subtle absorption lines on the quasar's spectrum, providing a detailed record of the conditions in the intergalactic medium. By analyzing these lines, astronomers can study the chemical composition, temperature, and density of the gas, as well as those that shaped the early universe. Cultural and philosophical reflections. The discovery of 3C273 and its implications go beyond science, touching on some of the deepest questions about our place in the universe. The realization that such powerful and distant objects exist forces us to confront the vastness of the cosmos and the smallness of our own existence. A beacon of wonder. For many, 3C273 is a symbol of the boundless potential of exploration. Its light, which began its journey billions of years ago, connects us to a time when the universe was far younger, reminding us of the continuity of cosmic history. This connection inspires a sense of wonder and curiosity, encouraging humanity to look beyond immediate concerns and imagine a future of discovery. The human desire to understand. The study of 3C273 exemplifies the human desire to make sense of the unknown. From the early observations that puzzled astronomers to the sophisticated analyses of today, the quasar's story is one of perseverance and ingenuity. It demonstrates how science can transcend the limits of perception, revealing truths that lie far beyond the reach of our senses. The future of 3C273 research. As we look to the future, the study of 3C273 will continue to evolve, driven by new technologies and scientific questions. The next generation of telescopes and observatories will allow astronomers to explore the quasar in greater detail than ever before, uncovering new layers of complexity and deepening our understanding of the universe. Space-based observatories. Future space missions, such as the Roman Space Telescope and the Advanced Telescope for High-Energy Astrophysics, Athena, will provide unparalleled views of quasars in multiple wavelengths. These observatories will allow scientists to study 3C-273's high-energy emissions and investigate the processes occurring near its supermassive black hole. Exploring the cosmic frontier. As humanity ventures further into space, 3C-273 and other quasars may serve as navigation beacons for interstellar spacecraft. Their brightness and stability make them ideal reference points for deep space exploration, ensuring that humanity's journey into the cosmos remains guided by the light of distant stars. A timeless inspiration. The light of 3C-273, traveling across billions of years, is more than just a scientific curiosity, it is a testament to the power of human imagination and determination. Its discovery and study remind us that the universe is vast, mysterious, and filled with wonders waiting to be uncovered. As we continue to explore the cosmos, 3C-273 will remain a guiding light, inspiring humanity to reach for the stars and embrace the infinite possibilities of discovery. Its journey is our journey, and as long as we seek to understand the universe, the brilliance of 3C-273 will continue to illuminate the way forward. A catalyst for future innovation. The discovery and ongoing study of 3C-273 demonstrate how one celestial object can drive advancements across multiple domains of science and technology. As humanity's understanding of quasars deepens, their influence will continue to ripple outward, inspiring new technologies, methodologies, and discoveries. Revolutionizing observational techniques. The unique properties of 3C-273, its brightness, variability, and accessibility, have made it an ideal candidate for testing and refining observational techniques. Over the decades, it has played a pivotal role in driving the development of advanced tools for studying distant celestial phenomena. High-resolution imaging. 3C-273 has been instrumental in the refinement of high-resolution imaging techniques, particularly interferometry. The ability to combine signals from multiple telescopes to create a single, detailed image has revolutionized our ability to study distant objects. The techniques developed to observe 3C-273 have since been applied to projects like the Event Horizon Telescope, which captured the first image of a black hole's event horizon. The same principles are now being adapted for space-based interferometry missions, which aim to achieve unprecedented resolution by positioning telescopes across vast distances in space. Such missions could allow astronomers to resolve fine details in the accretion disks and jets of quasars like 3C-273, providing new insights into their structure and dynamics. Multi-wavelength observations. The study of 3C-273 has underscored the importance of observing celestial objects across the entire electromagnetic spectrum. Each wavelength reveals a different aspect of the quasar, from the radio emissions of its jets to the X-rays produced near its black hole. Future observatories, such as the Cherenkov Telescope Array for gamma-ray astronomy and the Telescope for optical and infrared studies, will allow astronomers to probe 3C-273 with greater sensitivity and resolution than ever before. These observations will deepen our understanding of the physical processes driving its luminosity and variability. Expanding the frontiers of cosmology. Quasars like 3C273 are not just fascinating objects in their own right, they are also powerful tools for exploring the fundamental properties of the universe. As humanity continues to map the cosmos, 3C273 will remain a key reference point for studying large-scale structures, dark matter, and dark energy. Tracing the cosmic web. The light from 3C273 travels through billions of light-years of intergalactic space, passing through regions of gas and dark matter that make up the cosmic web. By studying the absorption lines imprinted on its spectrum, astronomers can map the distribution of matter across the universe. This work has profound implications for understanding the formation and evolution of galaxies, as well as the role of dark matter in shaping cosmic structures. The insights gained from 3C273 will contribute to a more comprehensive picture of the universe's history and its ongoing dynamics. Measuring cosmic expansion. The redshift of 3C273 not only reveals its distance but also provides a window into the expansion of the universe. By comparing the redshifts of quasars at different distances, astronomers can study the rate of cosmic expansion and refine models of dark energy, the mysterious force driving the acceleration of the universe. Future surveys of quasars, including those conducted by the Vera C. Rubin Observatory and the Euclid Space Telescope, will provide an unprecedented dataset for studying the interplay between dark energy, dark matter, and the growth of cosmic structures. 3C273, as one of the best-studied quasars, will serve as a benchmark for these efforts. Philosophical reflections on 3C273. The discovery of 3C273 transcends the boundaries of science, offering profound insights into humanity's place in the cosmos. It invites reflection on the nature of existence, the passage of time, and the interconnectedness of all things. A connection across time and space. The light we see from 3C273 today began its journey over 2 billion years ago, long before Earth was home to complex life. This temporal distance serves as a powerful reminder of the universe's vast timescales and our fleeting existence within it. It connects us to a distant past, offering a tangible link to a time when the universe was far younger. This perspective fosters a sense of humility and wonder, encouraging us to appreciate the interconnectedness of the cosmos. The photons emitted by 3C273's accretion disk have traveled across billions of light-years to reach our telescopes, carrying with them a story of immense power and beauty. Inspiring curiosity and exploration. The story of 3C273 exemplifies the power of curiosity and the human desire to understand the unknown. From its initial identification as a mysterious radio source to its role as a cornerstone of modern astrophysics, the quasar's journey reflects the best of human ingenuity and determination. It serves as a reminder that even the most perplexing phenomena can be understood through careful observation, collaboration, and innovation. This message resonates not only with scientists but with anyone who seeks to explore and understand the world around them. The future of 3C273. As we look to the future, 3C273 will continue to play a central role in the exploration of the universe. Its light, which has already traveled for billions of years, will serve as a guide for new generations of astronomers, physicists, and dreamers. A benchmark for discovery. As new technologies emerge, 3C273 will remain a benchmark for testing and refining our understanding of quasars and the extreme environments surrounding supermassive black holes. Its brightness and proximity make it an ideal target for next-generation telescopes and instruments, ensuring that it continues to yield valuable insights. A symbol of endless possibility. Beyond its scientific significance, 3C273 will remain a symbol of humanity's enduring quest for knowledge. Its light, shining across the vastness of space and time, reminds us of the infinite possibilities that lie beyond our current understanding. It encourages us to look upward, to question, and to explore. Conclusion: the eternal light of 3C273. The story of 3C273 is far from over. Its light, which has illuminated the universe for billions of years, will continue to guide humanity as we explore the cosmos. From its origins as a puzzling radio source to its role as a cornerstone of astrophysical research, 3C273 embodies the spirit of discovery and the boundless potential of human curiosity. As we gaze at the night sky and venture further into the universe, 3C273 will remain a beacon of inspiration, encouraging us to dream, to explore, and to embrace the mysteries of the cosmos. Its brilliance is a reminder that the universe is vast, beautiful, and full of wonders yet to be uncovered. In the light of 3C273, we find not only the story of a quasar but the story of humanity's endless journey to understand the infinite. The timeless journey of 3C273. As the light of 3C273 continues to traverse the cosmos, it serves as a bridge between the past and future, connecting the ancient universe to modern exploration. It stands as a living testament to the power of human curiosity and ingenuity, constantly revealing new mysteries and inspiring bold inquiries into the nature of existence. Beyond astronomy, broader scientific implications. The study of 3C273 has ripple effects that extend far beyond the realm of astronomy. The techniques, technologies, and theories developed to understand this quasar have influenced numerous other fields of science, technology, and even the humanities. It exemplifies how a single discovery can catalyze progress across disciplines. Applications in physics. The study of 3C273 has deepened our understanding of extreme physical processes, including relativistic jets, and the behavior of matter in the presence of intense gravitational and magnetic fields. These insights have been invaluable in refining our understanding of fundamental physics. For example, the study of jets emanating from 3C273 has provided empirical data to test and refine the theory of special and general relativity. The jets, which move at nearly the speed of light, demonstrate the effects of relativistic beaming and Doppler shifts, phenomena that are essential for understanding the behavior of particles and light near the speed of light. Informing particle physics. The high-energy particles in 3C273's jets mimic the conditions produced in human-made particle accelerators, such as CERN's Large Hadron Collider, LHC. Studying these jets allows scientists to observe natural particle acceleration processes on scales far larger than anything achievable on Earth. These observations inform the search for new particles and interactions, helping to bridge the gap between astrophysics and particle physics. Quasars as a window to the universe's future. While quasars like 3C273 primarily offer insights into the early universe, they also provide a glimpse into its future. The processes driving quasar activity, such as the growth of supermassive black holes and the evolution of galaxies, are ongoing, shaping the universe on timescales far longer than human history. The life cycle of quasars. 3C273 represents an active phase in the life of a galaxy, but this phase is not eternal. Over time, the supply of gas and dust feeding its supermassive black hole will diminish, causing the quasar to dim and transition into a quieter state. This transformation provides insights into the evolutionary pathways of galaxies, helping astronomers understand how quiescent galaxies like the Milky Way emerged from more active phases. The fate of the universe. The study of 3C273 and its counterparts also informs models of the universe's ultimate fate. By measuring the rate of cosmic expansion and the distribution of matter and energy, quasars provide data that shape our understanding of dark energy, the mysterious and the acceleration of the universe. These studies may one day answer fundamental questions about whether the universe will expand forever, collapse back into a singularity, or evolve in entirely unforeseen ways. A beacon for humanity's cosmic ambitions. As humanity prepares to explore beyond the confines of Earth, objects like 3C273 will play a crucial role in guiding us through the cosmos. Its brightness, stability, and distinct spectral characteristics make it an ideal celestial marker for interstellar navigation. Navigating the stars. In the future, spacecraft traveling between star systems may use quasars like 3C273 as navigational beacons. By measuring the precise positions and redshifts of multiple quasars, interstellar explorers could determine their location with incredible accuracy, even in the vast expanse of space. This capability will be essential for ensuring safe and efficient travel as humanity ventures further into the galaxy. A constant reminder of our origins. As we journey to other worlds, 3C273 will remain a constant presence, a reminder of our origins on Earth and our enduring connection to the universe. Its light, which has illuminated the cosmos for billions of years, will continue to guide us, offering a sense of continuity and purpose as we explore the unknown. Inspiration for future generations. The story of 3C273 is not just a scientific achievement, it is a narrative of exploration, creativity, and the human spirit. It embodies the values of perseverance, collaboration, and the relentless pursuit of knowledge, serving as an enduring source of inspiration for generations to come. Empowering education and outreach. Educational programs around the world use 3C273 as a case study to teach students about the universe's scale, the scientific method, and the power of observation. Its discovery story demonstrates how seemingly small questions, such as the origin of a faint radio signal, can lead to groundbreaking revelations that transform our understanding of reality. By sharing the story of 3C273 with the public, scientists and educators foster a sense of wonder and curiosity, encouraging people of all ages to engage with the mysteries of the cosmos. This engagement not only enriches individual lives but also strengthens the collective pursuit of knowledge and progress. Inspiring art and culture. The beauty and mystery of 3C273 have also inspired artists, writers, and philosophers to explore themes of light, distance, and time. Its light, which has traveled billions of years to reach us, symbolizes the interconnectedness of past, present, and future, offering a rich metaphor for human creativity in exploration. The eternal light of 3C273. As we look to the future, the significance of 3C273 will only grow. Its light, a gift from the ancient universe, will continue to illuminate new frontiers of knowledge, guiding humanity on its journey through the cosmos. A legacy of discovery. The discovery of 3C273 was a turning point in the history of astronomy, marking the dawn of a new era in our understanding of the universe. It revealed the true scale and complexity of the cosmos, challenging us to think bigger and reach further. This legacy of discovery will endure, inspiring future generations to ask bold questions, seek innovative solutions, and explore the farthest reaches of existence. In the brilliance of 3C273, we find a reflection of our own potential, a reminder that the universe is not only vast and mysterious but also full of endless possibilities. A future without limits. As humanity continues to explore the cosmos, 3C273 will remain a symbol of the boundless potential of science and imagination. Its light, shining across billions of years, is a beacon of hope and inspiration, encouraging us to dream beyond the horizon and embrace the infinite. The journey of 3C273 is a journey shared by all of us, a journey of discovery, wonder, and endless possibility. In the eternal light of 3C273, we find not only the story of a quasar but the story of humanity's enduring quest to understand the universe. Expanding our horizons, the future role of 3C273. As we venture deeper into the 21st century and beyond, 3C273 remains poised to play a pivotal role in advancing our understanding of the universe. Its unique characteristics, brightness, proximity, and historical significance, make it an enduring focal point for research, technological development, and philosophical reflection. Astrophysics in the age of precision. New observational technologies. The next generation of telescopes and observatories is set to revolutionize the study of quasars like 3C273. These cutting-edge instruments will provide unprecedented clarity and sensitivity, enabling astronomers to delve deeper into the processes that power quasars and the environments in which they exist. The Extremely Large Telescope, ELT, currently under construction, will have a 9-meter aperture, making it the largest optical and infrared telescope on Earth. With this extraordinary capability, astronomers will be able to resolve the intricate structure of 3C273's accretion disk and jets, shedding light on how supermassive black holes generate such immense energy. Similarly, space-based observatories like the James Webb Space Telescope, JWST, and upcoming missions such as the LUVOIR, Large UV Optical Infrared Surveyor, promise to open new windows into the high-energy regions surrounding 3C273. These telescopes will capture faint details invisible to ground-based systems, offering insights into the interaction between the quasar and its host galaxy. High-energy astrophysics. Quasars are among the most energetic phenomena in the universe, and 3C273 has become a cornerstone for studying high-energy processes. Future observatories like the Cherenkov Telescope Array, CTA, will provide an unprecedented look at gamma-ray emissions from 3C273, revealing the most extreme conditions near its supermassive black hole. These observations will contribute to our understanding of particle acceleration, magnetic fields, and the behavior of matter at relativistic speeds. The study of X-rays and gamma rays emitted by 3C273 will also allow scientists to probe the innermost regions of the accretion disk and understand how matter transitions from a stable orbit to a freefall into the event horizon. This exploration will deepen our understanding of the interplay between gravity, magnetism, and radiation in the universe's most extreme environments. Quasars as cosmic tools. 3C273 and its fellow quasars are not merely objects of study, they are also tools for exploring the larger universe. Their immense brightness and long lifetimes make them invaluable for addressing fundamental questions about the cosmos. Mapping cosmic distances. Quasars serve as cosmic lighthouses, illuminating the vast expanses of intergalactic space. Their redshifts provide a means of measuring cosmic distances and tracing the history of the universe's expansion. By studying 3C273 and similar quasars, astronomers refine the cosmic distance ladder, linking local measurements to the furthest reaches of the observable universe. This work contributes to our understanding of the Hubble constant, a critical parameter describing the rate of cosmic expansion. Resolving discrepancies in its measurement, known as the Hubble tension, is one of modern cosmology's most pressing challenges. The insights provided by 3C273 and its counterparts are essential for resolving this mystery. Probing the intergalactic medium. As the light from 3C273 traverses billions of light-years, it passes through vast clouds of intergalactic gas. These clouds leave fingerprints on the quasar's spectrum, providing information about the composition, temperature, and density of the intergalactic medium, IGM. The IGM is a critical component of the universe, serving as a reservoir of matter from which galaxies form and evolve. By studying how the light of 3C273 is absorbed and scattered by the IGM, astronomers gain insights into the universe's chemical enrichment and the processes that shaped its large-scale structure. The philosophy of 3C273. While the scientific contributions of 3C273 are profound, its discovery and study also invite deeper philosophical reflection. The light we see from 3C273 began its journey over 2 billion years ago, carrying with it a story of immense power and transformation. This temporal distance forces us to confront the enormity of the universe and our place within it. A cosmic perspective. The vast scales of time and space associated with 3C273 highlight the interconnectedness of the cosmos. Its light connects us to a distant epoch when the universe was younger and galaxies were still forming. This perspective encourages a sense of humility and wonder, reminding us that we are part of a continuum that stretches across billions of years. For many, 3C273 symbolizes the limitless potential of exploration and the enduring quest for understanding. Its brilliance challenges us to look beyond immediate concerns and consider the broader context of our existence. A symbol of human ingenuity. The story of 3C273 is a testament to the power of human curiosity and perseverance. From Martin Schmidt's groundbreaking analysis to the advanced studies of today, the quasar's journey reflects the best of scientific inquiry, the ability to observe, question, and innovate. A legacy of inspiration. The discovery of 3C273 has inspired generations of scientists, educators, and dreamers. It demonstrates that even the faintest signal can lead to profound revelations and that the pursuit of knowledge is an inherently rewarding endeavor. Educational programs frequently use 3C273 to teach concepts of astronomy, physics, and the scientific method. Its story illustrates the importance of curiosity, collaboration, and the willingness to challenge established ideas, encouraging students to explore their own questions about the universe. The eternal light of 3C273. As humanity continues its journey into the cosmos, 3C273 will remain a guiding light, both literally and figuratively. Its brilliance serves as a beacon of discovery, a reminder of the universe's infinite complexity, and a symbol of the boundless potential of human ingenuity. A timeless beacon. The light of 3C273 will continue to travel across the cosmos, outliving the civilizations and technologies that study it. Its story is one of endurance and transformation, mirroring the broader narrative of the universe itself. As long as there are those who look to the stars with curiosity and determination, 3C273 will remain a source of inspiration. A journey without end. The journey of 3C273 is far from over. Each new generation of scientists will build upon the discoveries of the past, uncovering new layers of complexity and forging new connections between this extraordinary quasar and the larger universe. Its light, traveling across billions of years, is a reminder that the quest for knowledge is never-ending, a journey as vast and beautiful as the cosmos itself. In the eternal light of 3C273, we find not only a window to the universe but also a reflection of our own limitless potential. The infinite lessons of 3C273. The story of 3C273 is not just about the discovery of a quasar, it is a profound narrative that encapsulates humanity's relationship with the cosmos. As we continue to study this remarkable object, it teaches us lessons about the universe's complexity, the power of scientific discovery, and our capacity for exploration. Unraveling cosmic mysteries. Quasars and galaxy evolution. The discovery of 3C273 revealed that quasars are not isolated phenomena but rather integral components of galaxy evolution. During their quasar phase, galaxies undergo significant transformations, driven by the activity of their central supermassive black holes. By studying 3C273, astronomers have learned that quasar activity often coincides with periods of intense star formation and galaxy mergers. These events feed the supermassive black hole with vast amounts of gas and dust, triggering the release of enormous energy. This energy, in turn, influences the surrounding galaxy by heating gas, suppressing star formation, or even expelling material into intergalactic space. This feedback mechanism has profound implications for our understanding of galaxy evolution. Quasars like 3C273 demonstrate how the smallest scales, those near a black hole, can shape the largest structures in the universe. Quasars and supermassive black holes. The study of 3C273 has also advanced our understanding of supermassive black holes, their growth, and their role in shaping the universe. These enigmatic objects, millions to billions of times the mass of the Sun, are now recognized as the engines driving quasar activity. Through detailed observations of 3C273's accretion disk and jets, scientists have gained insights into how black holes consume matter and convert it into energy. This process, known as accretion, is one of the most efficient ways of generating energy in the universe, far surpassing nuclear fusion. The study of 3C273 has also provided clues about the formation of supermassive black holes. One possibility is that these objects grew rapidly in the early universe through the mergers of smaller black holes and the accretion of surrounding matter. Observing quasars like 3C273 at different stages of their evolution helps refine these models and answer fundamental questions about the origins of these cosmic giants. 3C273 as a universal benchmark. As one of the brightest and most accessible quasars, 3C273 serves as a universal benchmark for studying high-energy astrophysics, cosmology, and galaxy dynamics. Its well-documented history and extensive data make it a reference point for testing new theories and technologies. Testing relativity and physics at extreme scales. The extreme environments near 3C273's black hole offer natural laboratories for testing the laws of physics under conditions that cannot be replicated on Earth. Observations of the quasar's jets, for instance, provide opportunities to study relativistic effects, such as time dilation, beaming, and energy transfer in high-velocity systems. These studies not only validate Einstein's theory of general relativity but also push the boundaries of our understanding of physics. They help identify where current theories may break down, offering clues about the need for new frameworks that unify general relativity with quantum mechanics. Cultural resonance of 3C273. Beyond its scientific importance, 3C273 has become a cultural icon, symbolizing humanity's quest for knowledge and our connection to the cosmos. Its light, which began its journey billions of years ago, serves as a metaphor for the enduring impact of discovery and the infinite potential of human creativity. Inspiring art and literature. The beauty and mystery of 3C273 have inspired artists, writers, and philosophers to explore themes of time, light, and the interconnectedness of the universe. Its story has been depicted in literature, documentaries, and visual art, offering new ways of understanding the cosmos and humanity's place within it. A symbol of exploration. 3C273 represents the spirit of exploration that drives humanity to look beyond immediate horizons. Its discovery reminds us that even the faintest signals can lead to profound revelations and that the act of questioning and observing is fundamental to progress. Future frontiers in 3C273 research. As technology advances and our understanding of the universe deepens, the study of 3C273 will continue to evolve. New instruments, missions, and methodologies promise to unlock even more secrets about this remarkable quasar and the broader universe. Advanced computational models. The increasing power of computational modeling is allowing scientists to simulate the conditions around 3C273 with remarkable accuracy. These models combine data from multiple wavelengths, radio, optical, X-ray, and gamma-ray, to recreate the dynamics of its accretion disk, jets, and surrounding environment. These simulations help answer questions about how matter behaves under extreme gravity and magnetism, shedding light on the processes that drive quasar activity. They also enable predictions about how 3C273 might evolve over millions of years, offering a glimpse into its future. Global collaborations and observatories. As astronomy becomes an increasingly collaborative field, global networks of observatories are working together to study objects like 3C273. Projects such as the Event Horizon Telescope and the Very Long Baseline Interferometry (VLBI) array bring together telescopes from around the world to create Earth-sized instruments capable of resolving the smallest details of distant quasars. These collaborations are not limited to ground-based observatories. Space-based missions, such as the James Webb Space Telescope, JWST, the European Space Agency's Athena X-ray Observatory, and future gamma-ray observatories, will complement ground-based efforts, providing a comprehensive view of 3C273 across the electromagnetic spectrum. A legacy without end. As humanity's understanding of the universe continues to expand, 3C273 remains a cornerstone of discovery and inspiration. Its light, which began its journey billions of years ago, connects us to the ancient universe while pointing toward a future filled with possibilities. A bridge across time. The photons emitted by 3C273's accretion disk serve as a bridge across time and space, linking the distant past to the present. As long as we study and reflect upon this extraordinary object, its light will continue to guide us, offering insights into the nature of the cosmos and our own place within it. A guide for the future. As we look toward interstellar exploration and the discovery of new worlds, 3C273 will remain a constant presence, a navigational marker, and a symbol of the infinite. Its brilliance will remind us of the universe's vastness, beauty, and mystery, encouraging us to embrace the unknown and continue our journey into the stars. Conclusion: the endless light of 3C273. The story of 3C273 is far more than the discovery of a quasar. It is a celebration of human curiosity, resilience, and ingenuity. Its light, traveling across billions of years, carries with it the lessons of the cosmos, offering a glimpse into the universe's past, present, and future. As we continue to study this extraordinary object, we are reminded that the universe is not just a collection of stars and galaxies but a dynamic, interconnected system filled with wonders waiting to be uncovered. The journey of 3C273 is a journey shared by all of humanity, a journey of discovery, imagination, and boundless possibility. In the eternal brilliance of 3C273, we find not only the story of a quasar but the story of ourselves, our universe, and our endless quest to understand the infinite. The ever-expanding legacy of 3C273. The story of 3C273 is a continuous unfolding narrative, reflecting the interconnectedness of science, technology, and the human spirit. As we delve deeper into the mysteries of this extraordinary quasar, its light illuminates paths to new discoveries and inspires a broader understanding of the cosmos and our place within it. The intersection of science and imagination. 3C273 is not just a scientific marvel, it is also a symbol of humanity's capacity for imagination and exploration. The quasar's journey from obscurity to prominence in scientific literature mirrors humanity's own journey of discovery, an ongoing quest to uncover the unknown. A spark for future innovations. The technologies developed to study 3C273 have spurred innovation across multiple fields, from advanced imaging techniques to computational astrophysics. These tools, initially designed to observe distant quasars, now have applications in diverse areas such as medical imaging, remote sensing, and artificial intelligence. For example, algorithms developed for analyzing the variability of quasars are now used in Earth-based applications, including climate modeling and natural disaster prediction. The ability to process and interpret vast datasets, honed through studies of 3C273, has become a cornerstone of modern scientific inquiry across disciplines. Deepening the study of black hole physics. At the heart of 3C273 lies one of the universe's most enigmatic phenomena, a supermassive black hole. The study of 3C273 continues to provide unprecedented insights into the nature of black holes, their accretion disks, and the high-energy processes that define their environments. Understanding black hole spin. One of the current frontiers in black hole research is the measurement of spin, a fundamental property that influences how a black hole interacts with its surroundings. The spin of 3C273's black hole affects the dynamics of its accretion disk, the energy of its jets, and the overall luminosity of the quasar. By analyzing the X-ray emissions from the inner edge of 3C273's accretion disk, astronomers aim to constrain the black hole's spin, providing insights into its formation history. High-spin black holes suggest rapid growth through accretion, while lower spin rates point to growth dominated by mergers. Quasars and the search for cosmic answers. Quasars like 3C273 are more than isolated objects, they are keys to unlocking some of the most profound questions in cosmology. Their light, traveling across billions of light-years, carries information about the universe's origins, structure, and ultimate fate. Exploring cosmic dawn. 3C273 provides a glimpse into an era when the universe was younger and more active. By comparing it to even more distant quasars, astronomers can piece together a timeline of cosmic history, from the first light of the reionization era to the large-scale structure we see today. Studying quasars helps address questions such as: how did the first galaxies and supermassive black holes form? What role did quasars play in shaping their host galaxies and surrounding environments? How do the processes observed in quasars like 3C273 inform our understanding of galaxy evolution? Quasars and the fate of the universe. The study of quasars also sheds light on the universe's long-term trajectory. Observations of 3C273 and similar objects contribute to our understanding of dark energy, the mysterious force driving the acceleration of cosmic expansion. By mapping the distribution and redshift of quasars, astronomers refine models of dark energy's behavior over time, providing clues about whether the universe will expand forever, slow to a halt, or collapse in a big crunch. Cultural and humanistic reflections. While the scientific significance of 3C273 is immense, its impact on culture and philosophy is equally profound. The quasar's light, which has traveled across billions of years, challenges us to think about time, existence, and our connection to the cosmos in new ways. A bridge between science and art. The awe-inspiring nature of 3C273 has inspired artists and writers to explore themes of light, time, and interconnectedness. It symbolizes the fusion of art and science, as both disciplines seek to make sense of the universe in their own ways. From poetry that captures the quasar's brilliance to visual art that reimagines its jets and accretion disk, 3C273 serves as a muse for creative expression. Its story reminds us that science is not just a pursuit of facts but also a source of wonder and inspiration. The philosophy of scale. The vast distances and timescales associated with 3C273 force us to confront the limits of human perception. Its light, which began its journey billions of years ago, connects us to a universe that existed long before humans walked the earth. This perspective emphasizes the continuity of existence and the interconnectedness of all things. At the same time, the discovery of 3C273 highlights humanity's ability to transcend those limits through curiosity and innovation. By observing and understanding a quasar so distant and powerful, we affirm our capacity to explore and comprehend even the most remote corners of the universe. The infinite potential of 3C273. The study of 3C273 is far from complete. As technology advances and our questions become more sophisticated, this quasar will continue to serve as a guide and a challenge, inviting us to push the boundaries of knowledge. A model for future discoveries. 3C273's well-documented history and extensive data make it an ideal model for studying other quasars and high-energy phenomena. Future telescopes and instruments will allow scientists to compare 3C273 with newly discovered quasars, identifying patterns and anomalies that deepen our understanding of these extraordinary objects. A guide for cosmic navigation. As humanity moves toward interstellar exploration, objects like 3C273 will play a practical role as navigational beacons. Their brightness and stability make them ideal reference points for spacecraft venturing beyond the solar system, ensuring accurate navigation in the vastness of space. A timeless symbol of exploration. The journey of 3C273 is a reflection of humanity's own journey, a story of discovery, resilience, and infinite curiosity. Its light, which has traveled across eons to reach us, serves as a reminder that the universe is vast, beautiful, and filled with mysteries waiting to be uncovered. A legacy of inspiration. As scientists, artists, and dreamers continue to explore the cosmos, 3C273 will remain a symbol of what is possible when we look beyond ourselves. Its brilliance, both literal and metaphorical, challenges us to dream big and think boldly. A journey without end. The light of 3C273 will continue to shine, guiding humanity through the challenges and triumphs of exploration. Its story is not just about a quasar, it is about the limitless potential of science, imagination, and the enduring quest to understand the universe. In the eternal light of 3C273, we see not just a quasar but the infinite possibilities of discovery and the unyielding brilliance of the human spirit. The expanding role of 3C273 in scientific exploration. As we continue to push the boundaries of astronomy and cosmology, 3C273 stands as a foundational pillar, offering insights into phenomena that are central to understanding the universe. Its multifaceted nature ensures that it will remain a focus of research across numerous scientific disciplines. Quasars and the evolution of the early universe. Quasars like 3C273 serve as time capsules, preserving the conditions of the early universe. The light from 3C273 has traveled over 2 billion years to reach us, providing a snapshot of a period when galaxies and black holes were actively evolving. Probing the epoch of reionization. The epoch of reionization marks the time when the first stars and galaxies began to form, ionizing the neutral hydrogen that filled the universe. 3C273 offers indirect evidence of this era by illuminating the intergalactic medium, IGM, it passes through. By studying its spectrum, astronomers can map the ionization history of the universe and identify the processes that led to the reionization of cosmic gas. This research addresses critical questions about the formation of the first structures in the universe and how they influenced the large-scale organization of matter we observe today. The birth and growth of supermassive black holes. One of the enduring mysteries in astrophysics is how supermassive black holes, like the one powering 3C273, formed so quickly after the Big Bang. Theories suggest that early black holes may have originated from the collapse of massive stars or the direct collapse of gas clouds. By studying the properties of 3C273 and comparing it to other quasars, scientists gain insights into the mechanisms that allowed these black holes to grow rapidly, whether through accretion of gas, mergers with other black holes, or a combination of processes. Understanding this growth helps us piece together the early stages of galaxy evolution and the role of black holes in shaping the cosmos. Unveiling the complexity of quasar jets. The relativistic jets emitted by 3C273 are among its most. These high-energy streams of particles, traveling at nearly the speed of light, extend for hundreds of thousands of light-years and are visible across multiple wavelengths. The physics of relativistic jets. Jets like those of 3C273 are believed to arise from interactions between the accretion disk and the magnetic fields surrounding the black hole. The particles in the jets are accelerated to near-light speeds, emitting radiation across the electromagnetic spectrum. Studying these jets provides insights into the mechanisms of particle acceleration, the role of magnetic fields in shaping jet dynamics, the impact of jets on the surrounding intergalactic medium, future high-resolution imaging, such as that enabled by the Event Horizon Telescope, EHT, and upcoming missions, will allow scientists to resolve the fine structures within these jets, providing a more detailed understanding of their origin and behavior. Jets as cosmic energy. The energy and material carried by quasar jets can influence their host galaxies and surrounding environments. In the case of 3C273, its jets are thought to heat and expel gas, regulating star formation and contributing to the chemical enrichment of the intergalactic medium. These interactions are critical for understanding the feedback mechanisms that govern galaxy evolution and the broader ecosystem of the universe. Quasars and the universal constants. Quasars like 3C273 are also valuable tools for probing fundamental constants of nature, such as the speed of light, the gravitational constant, and the fine structure constant. By analyzing the spectra of distant quasars, scientists can test whether these constants have remained stable over cosmic time. Probing the stability of physical laws. If variations in constants were detected, it would have profound implications for physics, suggesting that the laws governing the universe might evolve over time. 3C273, with its bright and well-studied spectrum, provides a reliable data source for conducting these tests. This research intersects with theories of quantum gravity, string theory, and other cutting-edge areas of physics, offering potential insights into the fundamental nature of reality. The role of 3C273 in big data astronomy. The vast amount of data generated by modern observatories has transformed astronomy into a field increasingly driven by big data. Quasars like 3C273 are central to this revolution, serving as key targets for large-scale surveys and computational analysis. Harnessing artificial intelligence. Artificial intelligence, AI, and machine learning algorithms are now used to analyze the variability, spectra, and light curves of 373 and other quasars. These tools can identify subtle patterns and correlations, uncovering relationships that might otherwise go unnoticed. For example, AI-driven analysis of 3C273's variability has provided new insights into the dynamics of its accretion disk and the physical processes driving its luminosity. These methods are becoming increasingly important as telescopes generate petabology. Citizen science and public engagement. Projects like Zooniverse have invited the public to contribute to the analysis of astronomical data, including observations of quasars. 3C273 has become a popular target for citizen scientists, who help identify patterns and anomalies in its behavior. This collaboration not only advances scientific research but also fosters a sense of connection between the public and the cosmos. 3C273 as a cosmic timekeeper. The regularity of 3C273's variability and its well-documented history make it a valuable tool for calibrating instruments and testing timekeeping in astrophysical observations. Its consistent brightness across billions of years allows scientists to compare data from different telescopes and epochs, ensuring accuracy and consistency. A standard candle for quasars. While supernovae are commonly used as standard candles for measuring cosmic distances, quasars like 3C273 are emerging as complementary tools. Their extreme brightness and detectability across vast distances are ideal for studying the far reaches of the universe. Future research aims to refine quasars as standard candles by identifying relationships between their luminosity and other observable properties. 3C273 is at the forefront of this effort, serving as a model for understanding quasar variability and its connection to intrinsic luminosity. A symbol of endless exploration. As we look to the future, 3C273 remains a symbol of humanity's unyielding drive to explore, understand, and innovate. Its light, traveling across billions of light-years, connects us to the distant past while guiding us toward the boundless possibilities of the future. An eternal beacon. The light of 3C273 will continue to shine for billions of years, outlasting the civilizations and technologies that study it. Its enduring brilliance reminds us that the universe is far larger and older than we can fully comprehend, yet within our reach to explore and understand. Inspiring generations to come. The story of 3C273 is one of curiosity, perseverance, and discovery. It challenges us to look beyond our immediate surroundings and embrace the vastness of the cosmos. For scientists, artists, educators, and dreamers, 3C273 is more than a quasar, it is a reminder of the infinite potential within each of us to seek knowledge and expand the boundaries of what is possible. Conclusion: the infinite light of 3C273. 3C273 is not merely a point of light in the constellation Virgo, it is a gateway to understanding the universe and our place within it. Its discovery and study have transformed astronomy, unveiling the dynamic and evolving nature of the cosmos. As we continue to study 3C273, its light will guide us toward deeper truths about the universe, its origins, and its future. It will inspire generations to look to the stars with curiosity and wonder, reminding us that the journey of discovery is as infinite as the cosmos itself. In the timeless light of 3C273, we find not only the story of a quasar but the story of humanity's enduring quest to illuminate the mysteries of existence. Expanding the reach of 3C273. The enduring significance of 3C273 lies in its ability to transcend the boundaries of scientific disciplines, influencing not only astronomy but also physics, mathematics, engineering, and even the humanities. Its light continues to spark curiosity, drive innovation, and inspire humanity's collective imagination. Quasars as beacons of universal connectivity. Quasars like 3C273 are some of the brightest objects in the universe, making them invaluable tools for understanding the large-scale structure and evolution of the cosmos. Their immense energy output and ability to shine across billions of light-years offer unparalleled opportunities for exploration. Mapping the universe with quasars as cosmic signposts that enable astronomers to map the distribution of galaxies, dark matter, and gas across the universe. By analyzing the positions and redshifts of quasars like 3C273, scientists construct three-dimensional maps of the cosmos, revealing its intricate web-like structure. These maps provide insights into the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. Galaxy clustering, the distribution and behavior of galaxies in relation to one another and their underlying dark matter halos. Cosmic evolution, how the universe's structure changes over time, influenced by the interplay of gravity, dark matter, and dark energy. The use of quasars in cosmic cartography is set to expand with upcoming surveys from the Vera C. Rubin Observatory and the Dark Energy Spectroscopic Instrument, DESI, both of which will target thousands of quasars to refine our understanding of the universe's structure. Illuminating intergalactic space. As the light from 3C273 travels across billions of light-years, it interacts with the intergalactic medium, IgM, the diffuse gas that fills the space between galaxies. These interactions leave imprints on the quasar's spectrum, offering a direct way to study the composition, temperature, and density of the IgM. By analyzing the absorption lines in 3C273's spectrum, astronomers can trace the distribution of hydrogen and heavier elements in the universe. Study the ionization history of the IgM, shedding light on the processes that shape the early. Explore how the IgM influences galaxy formation and evolution. This research connects the microphysics of individual particles with the macroscopic structure of the universe, demonstrating the interconnectedness of all cosmic phenomena. Technologies in quasar research. The study of 3C273 has driven the development of innovative technologies and methodologies that now benefit a wide range of scientific disciplines. High-precision spectroscopy. The analysis of 3C273's redshift and spectrum has spurred advancements in spectroscopy, allowing scientists to detect even the faintest signals across vast cosmic distances. Modern spectrographs, such as those used on the James Webb Space Telescope and the European Southern Observatory's Very Large Telescope, VLT, offer unparalleled sensitivity and resolution. These instruments have expanded the study of quasars by revealing signatures of elements first star, identifying the physical processes driving quasar variability and luminosity, measuring subtle variations in fundamental constants, such as the fine structure constant, time. Computational astrophysics. The complexity of quasar data has necessitated the development of sophisticated computational tools capable of modeling their behavior. Numerical simulations of 3C273's accretion disk, jets, and host galaxy offer valuable insights into the physical processes at work, while machine learning algorithms uncover hidden patterns in observational data. These advancements are not limited to astronomy. The same computational techniques are now applied in fields ranging from climate modeling to medical diagnostics, demonstrating the broad impact of quasar research. Quasars and fundamental physics. Quasars like 3C273 provide natural laboratories for testing fundamental theories of physics under extreme conditions. Probing relativity and black hole dynamics. The extreme environments near 273's black hole offer unique opportunities to test Einstein's theory of general relativity. By studying the motion of matter in its accretion disk and the behavior of light near the event horizon, scientists can explore the effects of intense gravity on space and time. Observations of 3C273 have already confirmed key predictions of relativity, such as the bending of light in strong gravitational fields, the time dilation experienced by particles near the black hole, the energy shifts caused by relativistic motion. Future observations with instruments like the Event Horizon Telescope and space-based X-ray observatories will allow even more precise tests, potentially uncovering deviations from relativity that hint at new physics. Understanding high-energy phenomena. The jets of 3C273 produce radiation across the electromagnetic spectrum, including high-energy gamma rays. These emissions provide a window into particle acceleration field dynamics, offering clues about processes that also occur in phenomena like supernovae, pulsars, and cosmic rays. Studying these high-energy processes helps bridge the gap between astrophysics and particle physics, contributing to our understanding of fundamental forces and interactions. A timeless inspiration for humanity. Beyond its scientific contributions, 3C273 holds a special place in the human imagination. Its discovery represents a triumph of ingenuity, reminding us that the universe is both vast and accessible through exploration. A story of discovery. The journey of 3C273 from an unremarkable radio source to a cornerstone of modern astrophysics exemplifies the scientific process. 1. Observation. Early radio surveys identified 3C270 sources of interest. 2. Hypothesis. Astronomers speculated about its nature, considering possibilities from stars to distant galaxies. 3. Analysis. Martin Schmidt's groundbreaking analysis of its spectrum revealed its true distance and luminosity. 4. Revolution. The discovery of 3C273 transformed our understanding of the universe, introducing the concept of quasars and the role of supermassive black holes. This story continues to inspire scientists and educators, demonstrating how careful observation and critical thinking can lead to transformative discoveries. A beacon of wonder. For those who gaze at the night sky, 3C273 is more than just a point of light, it is a symbol of humanity's enduring connection to the cosmos. Its light, which began its journey billions of years ago, bridges the vast gulf of time and space, reminding us of our place in a universe filled with mysteries. As we continue to extend 3C273, its brilliance will guide us, encouraging us to look beyond the limits of our knowledge and embrace the infinite possibilities of discovery. Conclusion: the endless journey of 3C273. The C273 is a testament to humanity's capacity for curiosity, innovation, and exploration. Its light, traveling across billions of years, carries with it the secrets of the universe and the promise of future revelations. As we continue to study this extraordinary quasar, it will remain a beacon of inspiration, reminding us that the universe is vast, beautiful, and filled with to be uncovered. In the light of 3C273, we see not just the story of a quasar but the story of humanity's infinite journey to understand the cosmos and our place within it. The Milky Way is not alone. Surrounding our galaxy is a vast halo populated by numerous smaller galaxies, its satellites, that orbit it like moths around a flame. These galactic companions are remnants of an ancient past, relics of cosmic evolution stretching back billions of years, and they serve as natural laboratories for understanding dark matter, star formation, and the hierarchical growth of galaxies. Among the most prominent of these satellites are the large and small Magellanic clouds, visible to the naked eye from the southern hemisphere. These irregular galaxies are in the midst of a gravitational dance with the Milky Way, trailing long streams of gas, known as the Magellanic Stream, across the sky. This gaseous ribbon, shaped by tidal forces and ram pressure, may fuel future star formation galaxy's disk. Other satellites, the Sagittarius dwarf spheroidal galaxy, tell tales of cosmic cannibalism. Sagittarius is currently being torn apart by the Milky Way's its stars stretched into long, looping streams that wrap around our galaxy. This ongoing merger provides direct evidence of how large galaxies grow, by accreting smaller ones. Traces of other past mergers are etched into the stellar halo of the Milky Way in the substructures, stellar fossils of ancient galaxies long since consumed. Most of the Milky Way's satellites are dwarf spheroidal galaxies, such as Draco, Ursa Minor, Sculptor, and Fornax. These faint, low-mass systems are dominated by dark matter and have very little gas, often hosting only ancient, metal-poor stars. Their simplicity makes them testbeds for studying the influence of dark matter on galactic dynamics. Some of these dwarfs show signs of past bursts of star formation, while others appear to have been quenched early, possibly due to environmental effects from the Milky Way's hot halo or reionization in the early universe. Ultra-faint dwarf galaxies, discovered more recently thanks to deep sky surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, are among the most dark matter-dominated systems known. With only a few thousand stars, yet massive dark halos, they challenge our understanding of galaxy formation and provide key constraints on the nature of dark matter itself. Their existence also helps to resolve the so-called missing satellites problem, a long-standing tension between the large number of predicted dark matter subhalos and the smaller number of observed dwarf galaxies. These satellite galaxies are more than mere curiosities. They also serve as unique probes into the broader cosmological landscape. By measuring the movements of stars within these dwarf companions, astronomers can intuition and quantity of dark matter around the Milky Way. This helps refine theoretical models that predict how galaxies form and evolve over cosmic time. Additionally, satellite galaxies hold crucial clues about the early universe. Their oldest star, nearly as ancient as the universe, observe chemical fingerprints that reflect under which the first generation formed. Studying their metallicity, the abundance of elements heavier than helium, allows scientists to reconstruct star formation histories and better understand processes like chemical enrichment across cosmic epochs. Moreover, satellite galaxies can trigger significant transformations in their larger host. For example, interactions between the Magellanic clouds and the Milky Way can induce resonances and disturbances in our galaxy's outer disk. Recent studies suggest these interactions may even warp the Milky Way's late episodic star-forming events. This complex gravitational interplay showcases the intricate dance between galaxies and their influencing each other's evolution profoundly. Intriguingly, the distribution of satellite galaxies around the Milky Way has sparked about cosmic structure. Observations suggest many satellites are aligned in planar structures, such as the so-called plane of satellites. This arrangement is at odds with predictions from standard cosmological models, which expect a more isotropic or spherical distribution. The presence of these satellite planes has fueled alternative hypotheses, including scenarios where the satellites formed from ancient collisions or were gravitationally captured groups of galaxies traveling together through intergalactic space. Recent advances in telescopes, like Gaia and JWST, have allowed us to peer deeper into these galaxies, mapping their structures and stellar motions with unprecedented precision. Gaia's precise astrometry detailed orbitals, helping astronomers how satellites will move, and how some might eventually merge completely into the Milky Way. Meanwhile, JWST's sensitive infrared capabilities are enabling astronomers to observe the faintest, oldest stellar populations in these satellites, pushing our understanding of the early cosmic epochs even further back in time. These galactic companions are not simply passive neighbors, rather, they actively shape and inform our understanding of cosmology, galaxy formation, and the mysterious nature of dark matter. The ongoing exploration of our galaxy's satellite system promises many more revelations, shedding light on the dynamic history and intricate structure of the cosmic web that connects all galaxies, large and small. Further deepening this cosmic mystery are interactions between satellite galaxies themselves. Indicate that satellites can gravitationally influence each other, altering orbits, formation, or accelerating the process of galactic For example, the Magellanic, as a binary system orbiting the Milky Way, act dynamically with each other, complicating their orbital evolution and leaving complex tidal signatures in their stars and gas clouds. Additionally, dwarf satellite galaxies often host compact star clusters called globular clusters. These clusters are dense, gravitationally bound systems, containing hundreds of thousands of stars, and often outlive their parent galaxies. When their host dwarf galaxies disintegrate under gravitational forces, these globular clusters can be left orbiting the Milky Way independently, providing astronomers with clues to reconstruct the history of past galactic mergers and accretions. Another fascinating aspect of satellite galaxies is their role in constraining the nature of dark matter itself. High dark matter densities, dwarf spheroidal galaxies ideal testing grounds for different models. Some astrophysicists have explored alternatives to standard matter (CDM) models, such as warm dark matter or self-interacting dark matter, to explain discrepancies between theoretical and observations of satellite galaxy structures. The density profiles and internal dynamics of these dwarfs can distinguish among competing theoretical frameworks. The future of satellite galaxy research is bright, with upcoming telescopes and surveys promising to detect even fainter galaxies around the Milky Way. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, slated to start observations soon, will significantly expand our catalog of known satellite galaxies. LSST's comprehensive sky coverage and unprecedented sensitivity will allow astronomers to detect ultra-faint satellites previously beyond reach, offering a more complete census of the Milky Way's galactic. These discover the handling of how galaxies evolve but also offer insight into shaping the universe at large. As astronomers peer deeper into our galaxy's satellite system, each tiny dwarf galaxy becomes a crucial puzzle piece in revealing the grand story of cosmic evolution. From the earliest moments after the Big Bang to the present-day gravity, dark matter, gas, and stars. Satellite galaxies, therefore, are key witnesses and future of our galactic environment, guiding humanity in understanding our own cosmic origins and destiny in an ever-expanding universe. The mysteries surrounding satellite galaxies also extend to their formation processes. According to physical models, small galaxies form the universe, eventually merging through gravitational interactions to build larger structures. Observations of our Milky Way's satellites support this hierarchical model, providing direct evidence of ancient mergers embedded within their stellar populations. By analyzing their chemical compositions and stellar, astronomers have uncovered unique evolutionary paths, each dwarf galaxy representing a distinct piece of our galactic heritage. One particularly compelling area of research involves tracing stellar archaeology, the study of satellite galaxies. Stars preserve within their atmospheres the chemical signatures of the environment in which they formed, effectively in the history of their parent galaxies. Some satellite galaxies host remarkably pristine stars with extremely low metal content, links to the earliest epochs of cosmic history, providing insight into conditions shortly after the Big Bang. Moreover, recent studies have found evidence of black holes and dwarf galaxies, challenging long-held assumptions that such massive objects exist predominantly in larger galaxies. For instance, intermediate holes from thousands of solar masses might reside quietly at the centers of certain satellite galaxies. Detecting and understanding these elusive black holes is crucial for reconstructing how black holes form and grow, bridging gaps in our understanding of supermassive black hole evolution and their relationship to galaxy formation. Furthermore, the Milky Way's hot gas halo and its satellite galaxies have profound implications for galaxy evolution. The gas within satellite galaxies can be stripped away by the ram pressure exerted as they move through the Milky Way's circumgalactic medium. This environmental process explains why many satellites today appear devoid of stars and thus remain in a dormant. Observations of neutral hydrogen distributions and gas dynamics in satellites further illuminate the intricate balance between gravitational forces, hydrodynamics, and galactic. Recent cosmological simulations such as Illustris and Eagle have significantly advanced our understanding of these dwarf galaxies by modeling their formation, evolution, and destruction with unprecedented detail. These simulations not only the general population of observed satellite galaxies but also their detailed structural and chemical properties. They reveal the complex interplay between star formation feedback, gas removal, tidal disruption, and dark matter dynamics shaping the dwarf galaxies we see today. Satellite galaxies also have cosmological implications beyond our own Milky Way. Studies of satellites around other large galaxies, like Andromeda and M31, have revealed striking parallels and differences that inform universal principles of galaxy assembly and evolution. The satellite systems of Milky Way-like galaxies serve as cosmic laboratories, helping astronomers test whether the observed properties of satellite galaxies around our home galaxy represent universal trends or unique phenomena. This growing body suggests that our understanding of satellite galaxies will remain pivotal to unraveling deeper cosmological mysteries. Each new discovery, whether from observational breakthroughs or sophisticated computational modeling, pushes the boundaries of astrophysics and cosmology, ultimately bringing clarity to our place within the broader cosmic framework. As astronomers continue exploring satellite galaxies, one fascinating puzzle that emerges is their potential role in solving the long-standing question of cosmic reionization. Early in the universe's history, neutral hydrogen gas filled intergalactic space visibility and creating a cosmic. Gradually, the first stars and galaxies emitted energetic radiation, ionizing this hydrogen gas and making the universe transparent, a period known as the Epoch of Reionization. Although massive galaxies have often been credited with driving reionization, recent studies suggest that small satellite galaxies, including ultra-faint dwarfs, may have collectively played a crucial role, providing sufficient ultraviolet photons to transform the cosmos. Furthermore, satellite galaxies can shed light on the elusive question of dark matter properties. Some theories predict specific signatures, like gamma rays from dark matter annihilation, within these species, due to their dense dark matter core. By observing gamma-ray emissions from dwarf satellites using sensitive telescopes such as the Fermi Gamma-Ray Space Telescope or future observatories like the Cherenkov Telescope Array, astronomers hope to detect indirect signals of dark matter particles, a breakthrough that could revolutionize physics. The phenomenon known as tidal stripping further enriches the narrative surrounding satellite galaxies. Dwarfs orbit close to their massive hosts. Gravitational tides gradually remove outer layers of stars and gas, leaving behind stellar streams as tangible remnants of galactic disruption. Mapping these streams provides a precise record of how satellites apart over cosmic time, enabling astronomers to reconstruct detailed orbital histories. Such tidal features not only chronicle past interactions but also probe the gravitational potential of galaxies. Additionally, satellite galaxies can act as windows into the enigmatic nature of globular cluster formation. Some globular clusters originally formed in dwarf satellites, later gravitationally unbound the Milky Way's halo. Stars' chemical compositions, orbits, and stellar populations allows astronomers to identify their original dwarf hosts and unravel a complex story of migration, accretion, and galaxy assembly that spans billions of years. The future exploration of satellite galaxies holds a special generation telescopes on these like Large Telescope, E.L. Nancy Grace Roman Space Telescope, and advanced radio capable faintest dwarf galaxies lurking at the edges of the Milky Way's gravitational reach, uncovering structures that have remained hidden since the universe's infancy. Moreover, upcoming gravitational wave of LISA, laser space antenna, could detect signals from intermediate mass black holes residing within dwarf satellites, directly connecting dwarf galaxy evolution with black hole growth scenarios. Such detections would bridge observational astronomy and gravitational wave astrophysics, enhancing our understanding of galaxy formation observational fronts. These investigations underscore the essential role satellites play, not only as intriguing cosmic neighbors but as powerful tools for unlocking profound scientific questions. From the earliest cosmic dawn to the complex interplay of gravity, matter, and radiation today, satellites continue to serve as beacons of cosmic insight, guiding our exploration of the universe's deepest mysteries. Satellites also provide astronomers sights into the cosmos, the idea that the universe is homogeneous and isotropic on large scales. The peculiar planar alignment observed among Milky Way satellites, and similarly noted around galaxies like Andromeda and Centaurus A, poses a direct challenge to principle. Standard cosmological models anticipate spherical distribution. The apparent relations prompt intriguing questions about galaxy assembly processes and potential deviations from conventional cosmology. Whether these alignments represent temporary, chance occurrences or signify deeper, yet undiscovered physical phenomena remain these compelling open questions. In addition, dwarf galaxies' star formation chemical abundances offer precious windows into the stellar feedback processes critical for regulating galaxy growth. The smallest satellites, with shallow wells, are extremely sensitive to star formation-driven winds. Massive stars, upon ending their lives in supernova explosions, inject enormous amounts of energy, expelling gas, and even halting future star formation altogether. By analyzing how effectively stellar feedback operates in these low-mass systems, astronomers refine star formation and feedback, understanding of galaxy evolution across all scales. The distribution satellite further enriched narrative. Satellites typically host metal-poor stellar populations, reflecting early epochs when few heavy elements existed. However, subtle variations in chemical enrichment patterns among satellites, such as differences between the Magellanic Clouds and ultra-faint dwarfs, reveal unique evolutionary paths of their environment and star formation histories. Decoding these chemical signatures allows astronomers to reconstruct precise sequences of stellar birth, death, and enrichment events, ultimately providing detailed timelines of galactic evolution. Furthermore, recent observations using space-based observatories have identified satellite galaxies orbiting around other distant galaxies in galaxy clusters and groups. By comparing these extragalactic satellites with those around them, astronomers can investigate how influences satellite galaxy properties universally. Studies reveal striking similarities and notable differences, helping angle local environmental effects from universal cosmological processes. Such comparative research is essential for contextualizing our galaxy's satellite system within the broader landscape of galaxy evolution across cosmic environments. Satellite galaxies may also help unravel the nature of cosmation and dark energy. By mapping precise satellite motions around their host galaxies, astronomers can measure subtle changes in orbital dynamics potentially influenced by dark energy's impact on cosmic structure formation. While challenging, this method could provide novel independent constraints on dark energy models, complementing large-scale cosmological surveys. Moreover, observations and observational studies are increasingly exploring how satellite galaxies affect galactic habitable zones. Tidal interactions between massive galaxies and their satellites could induce episodes of star supernova explosions or bursts, dramatically affecting habitability conditions in planetary systems. Understanding the interplay between galaxies and their satellite companions might thus offer valuable clues about habitability and the emergence of life elsewhere in the universe. As satellite galaxy research continues evolving, physics or biology are emerging. Each dwarf galaxy, though small and faint, holds answers to some of humanity's most profound questions: the nature of dark matter, the origins and evolution of galaxies, the conditions enabling planetary habitability, and the fundamental architecture of our cosmos. Satellite galaxies also highlight the subtle yet crucial interplay between evolution and explored domains. Recent studies suggest that even dwarf galaxies, despite their low stellar densities and gas content, may harbor weak magnetic fields. Detecting magnetic faint satellites could revolutionize our understanding of cosmos and how different scale of gas. Additionally, the process known as galaxy quenching, where abruptly ceases, in exceptional detail like galaxies lose their gas reservoirs through tidal stripping, ram pressure, or internal feedback, astronomers gain deeper insights into mechanisms responsible for halting star formation. Investigations into this process within satellites help refine broader theories about how and why galaxies stop forming stars, a central mystery in galactic evolution. Satellite galaxies also offer exceptional tools for testing modified gravity theories, which propose alternatives to Einstein's general relativity to explain cosmic acceleration or dark matter phenomena. The precise orbital motions of dwarf satellites around the Milky Way provide stringent gravitational interactions at galactic scales. Careful measurement of these motions, achieved through Gaia's high-precision astrometry, allows astronomers to rigorously test predictions from theories such as Newtonian dynamics, reshaping our understanding of gravity's fundamental nature. Beyond our Milky Way, studies of satellite galaxies orbiting giant elliptical galaxies in galaxy clusters like Virgo or Fornax reveal additional layers of complexity. These satellites, embedded in dense cluster environments, often undergo accelerated evolution due to intentional interactions, galaxy harassment, and rapid gas removal. By contrasting satellites in these dense environments with those orbiting the relatively isolated Milky Way, astronomers discern how local conditions profoundly shape galaxy evolution. Satellite galaxies even in standing of high-energy particles traversing space. Cosmic ray production and propagation within and between galaxies may be influenced by satellite-host interactions, supernova explosions, or starburst episodes triggered by dwarf galaxy mergers. Studying cosmic rays emanating from dwarf galaxies or stellar streams enriches our comprehension of how these energetic particles move through intergalactic space and influence galactic ecosystems. Moreover, dwarf galaxies could serve as ideal laboratories to study extreme stellar phenomena, such as luminous supernovae or neutron star. Their relatively simple structures and reduced stellar populations allow astronomers to trace these dramatic events back to specific star formation conditions, providing unique insights into stellar evolution, nucleosynthesis, and gravitational wave astronomy. Finally, as we explore deeper into our galactic neighborhood, new mysteries continually arise. The persistent discovery of ultra-faint satellites around the Milky Way challenges predictions from cosmological simulations, prompting theorists to reconsider assumptions about the distribution and properties of dark matter. As observational precision grows, satellite galaxies continue serving as invaluable testing grounds, probing and refining our most fundamental theories itself. Satellite galaxies further connect astronomers to the intricate structures of the cosmic web, the vast network of dark matter filaments interconnecting the universe. Simulations suggest that dwarf galaxies eventually form along these dark matter filaments gravitationally bound to larger hosts like spatial distribution, orbital dynamics, and chemical properties of these provides astronomers with powerful insights into how galaxies trace the large structure, offering clues about both visible matter and dark matter backbone of the universe. Furthermore, detailed analyses of satellite galaxies can enhance our understanding of galaxy disks and stellar halos. Satellites occasionally disturb their host galaxies, creating subtle ripples, warps, or spiral density waves in the disk structure. Evidence of past interactions can be observed directly in our Milky Way, where perturbed by satellite provide insight into the mass distribution, dynamics, and evolutionary history of our galactic home. In other words, satellites act like tiny gravitational seismographs, allowing astronomers to measure the otherwise invisible massive galaxy host. Recent studies also suggest intriguing connections between dwarf satellite galaxies and fast radio bursts, FRBs, powerful radio pulses from distant cosmic sources. Although FRBs remain mysterious, some theories propose they may originate from magnetars, highly magnetized neutron stars, formed after supernovae in dwarf galaxies. Satellite galaxies, due to their lower metallicities and unique star formation histories, could thus provide ideal environments for producing and studying phenomena, potentially revolutionizing of neutron star evolution, extreme astrophysics, and the nature of transients. The exploration of satellite galaxies is not limited solely to observational astronomy. Astrobiologists speculate that dwarf galaxies might influence the habitability of planets in their larger hosts by triggering episodic galactic events, gamma-ray bursts or periods of intense star formation, potentially shaping evolutionary pathways on habitable worlds. This emerging interdisciplinary field, linking satellite galaxy studies with astrobiology, underscores how deeply interconnected cosmic scales of galaxies to planets are. Satellite galaxies also shed light on the physics of circumgalactic media, CGM, the vast reservoirs of diffuse gas surrounding galaxies. By interacting dynamically with their host CGM, satellites experience gas stripping or accretion events, providing observational evidence of this other visible gas component. Understanding the interplay between dwarf galaxies and CGM is vital for accurately modeling galaxy evolution, gas recycling, and star formation processes in galaxies across cosmic time. On another frontier, dwarf galaxies can serve as benchmarks for calibrating cosmological simulations. As powerful tools attempt to reproduce the complex details of galactic evolution, from star formation feedback to dark matter distributions, the observed property galaxies become stringent tests of these simulations' accuracy. The precise agreement or disagreement between models guides improvements in our understanding of galaxy formation, cosmology, and fundamental physics. Moreover, satellite galaxies baryonic relation, a fundamental correlation linking galaxy rotation velocities to baryonic mass. Traditionally studied in massive galaxies, whether it's physics and math challenge standard scenarios, pushing the boundary of theory. Ultimately, the continued study of satellite galaxies is becoming increasingly interdisciplinary, incorporating observational astronomy, theoretical astrophysics, computational modeling, particle physics, and even philosophical reflection. Each dwarf galaxy represents a distinct story, its stars, gas, dark matter, and chemical elements encoding cosmic narratives that span nearly the entire history of the universe. As we uncover these narratives, we gain profound insights into the universe's past, present, and future. These connection to the cosmos. Light gallo enable astronomers to phenomena such as star cluster dissolution, tidal heating, and in dynamics in extraordinary detail. Within the gravitational environment of a massive galaxy like the Milky Way, dwarf satellites face immense tidal stresses, affecting their internal structures. Detailed studies of tidal deformation astronomers to quantify precisely how stars migrate within galaxies, how stars disperse into stellar streams, and how galaxies dynamically evolve under gravitational interactions. This information illuminates fundamental processes governing stellar distribution and galaxy evolution on all scales. In addition, dwarf galaxies provide exceptional opportunities for studying stellar population gradients and internal structure formation. Many satellites exhibit variations in stellar age, metallicity, and chemical composition across their spatial extent. By mapping these subtle gradients, astronomers unravel how galaxies grow and evolve, from their dense cores outward to their tenuous outskirts. Such detailed population analyses enrich our understanding of how environmental factors, like tidal interactions and ram pressure stripping, shape galaxies' internal properties over cosmic time. Satellite galaxies also inform cosmological inquiry into the abundance and properties of primordial, hypothesized remnants formed shortly after the Big Bang. Some cosmologists propose that dwarf galaxies might preferentially host these elusive objects, potentially serving as gravitational lenses or dark matter candidates. Observations of micro or anomalous gravitational signals from satellites could therefore light on the existence and cosmological significance of primordial black holes, providing invaluable tests of early universe physics. Moreover, dwarf satellites play a crucial role in galaxy scaling relations, such as the mass-metallicity relationship, galaxy's total stellar mass to its heavy element abundance. While well established for large galaxies, observing whether dwarf galaxies strictly adhere to or deviate from these relations allows astronomers galaxy formation theories, refine chemical evolution models, and better understand how galaxies enrich themselves chemically throughout cosmic history. From a theoretical perspective, satellite galaxies are essential to robust formation scenarios under different cosmological conditions. Various cosmological simulations explore alternative universes with differing physical parameters, such as dark matter properties, gravitational theories, or feedback mechanisms. By comparing the simulated properties of satellite galaxies, such as size, density profiles, and star trajectories, to observational data, astronomers understand of cosmological constants and the fundamental laws shaping galaxy evolution. Furthermore, satellite galaxies may help astronomers pinpoint precise details about the nature and stellar remnants, such as white neutron stars and quark stars. Low mass, faint dwarf galaxies provide pristine environments for observing these exotic objects due to their minimal stellar populations and simple backgrounds. Studying remnants within dwarf satellites offers unique windows into extreme stellar evolution, compact object formation, and intergalactic environments. Advancing further, researchers increasingly employ machine learning techniques and artificial intelligence algorithms to identify and analyze satellite galaxies. Advanced computational methods rapid observational datasets from modern telescopes, detecting ultra-faint galaxies previously hidden within data noise. These tools accelerate, enhance precision, and reveal subtle satellite distribution properties, pushing galaxy studies into a new era of data-driven astronomy. The continuing investigation of satellite galaxies demonstrates a remarkable truth: these small cosmic neighbors are far more than mere companions to the Milky Way. They represent key history of the cosmos, tightly woven with profound mysteries of astrophysics, cosmology, and fundamental physics. Each of these galaxies not only enriches our cosmic perspective but also deepens humanity's understanding of our place in the universe. Satellite galaxies also serve as ideal laboratories for investigating cosmic metallicity floors, the lowest possible abundances of heavy elements achievable in galaxies. Ultra-faint dwarf galaxies, due to their extremely limited star formation, retain ancient stars nearly unaltered since their formation billions of years ago. By examining these stars' chemical conditions, astronomers insights into early nucleosynthesis, the creation of stellar generations, thereby reconstructing the chemical evolution of the universe from its infancy onward. Further extending their satellite galaxies provide a unique vantage point for studying dwarf galaxy luminosity functions. This distribution, describing how many dwarf galaxies exist at various luminosities, profoundly impacts cosmological models. Observational satellites to rigorously test predictions from cold dark matter cosmology, regularly addressing persistent theoretical issues like the too big to fail problem, which concerns discrepancies between the observed numbers of bright satellites and those predicted by simulations. Satellite galaxies may even offer critical insights into phenomena like galaxy-galaxy lensing, a gravitational lensing effect in which galaxy bend background sources. Dwarf satellites, orbiting massive galaxies, subtly modify gravitational lensing signatures, providing precise galaxy mass profiles and dark matter halo shapes. Carefully studied effects refines our understanding of galaxy mass distribution significantly to unraveling the true nature and distribution of dark matter. Additionally, dwarf satellites challenge and enhance current understandings of galaxy rotation curves, plots describing how orbital velocity changes with galaxy centers. Unlike large spiral galaxies exhibit rotation curves that diverge significantly from theoretical expectations based purely on visible matter. By thoroughly examining rotation dynamics in these dwarfs, astronomers dark matter distribution models, test alternative gravity theories, and refine our understanding of the laws governing galactic motion at small scales. Moreover, satellite galaxies serve as excellent observational targets for studying stellar feedback at the smallest galactic scales. The small gravitational waves amplify the effects of feedback mechanisms, such as supernova explosions or stellar winds, dramatically influencing their evolution. Observing how feedback disrupts gas reservoirs, shapes stellars, and regulates stars, astronomers develop theoretical frameworks applicable not only to dwarfs but to galaxies across the hierarchy. Satellite galaxies also illuminate critical aspects of the cosmic baryon cycle, the continual movement of ordinary matter, gas, in and out of galaxies. As dwarf satellites orbit their host galaxies, they frequently lose their gas, sometimes feeding the medium, CGM, or even the intergalactic medium. Tracking this movement offers direct observational constraints on gas exchange processes, improving our understanding of how galaxies gain and lose gas, regulate and evolve chemically over cosmic timescales. In addition, satellites can function as invaluable indicators of the cosmic ultraviolet and energetic radiation field permeating the universe. By observing how ultraviolet radiation impacts satellite galaxies' star formation, gas content, and stellar populations, astronomers reflect of this radiation's evolution through cosmic history, from the reionization epoch to today. Such research bridges studies of galaxy evolution with broader cosmic processes, providing an integrated understanding of cosmic history. As astronomers, their intensive study of seas, these cosmic entities are recognized as central players in astrophysics. Their hidden secrets, accessible through advanced observations, computer simulations, and theoretical analyses, continually redefine humanity of compelling scientific alike to rethink our place within this vast universe. Ultimately, the satellite galaxies orbiting the Milky Way represent far more than mere cosmic neighborhood. They are profound windows into the earliest moments of cosmic history, extraordinary physics, and key puzzle pieces for unraveling the mysterious nature and galaxy evolution. Their faint starlight, ancient stars, and delicate structures record billions of years of cosmic interplay, preserving clues about how galaxies form, evolve, and interact across the expanse of the universe. Future observations, harnessing powerful next-generation telescopes such as the Vera Rubin Observatory, the Extremely Large Telescope (ELT) and advanced space-based observatories, promised celestial objects into unprecedented clarity. New surveys will detect even fainter satellite galaxies, uncovering previously hidden populations, pushing the boundaries of our understanding of dark matter, galactic interactions, stellar evolution, and the very conditions that enabled our existence. Satellite galaxies will continue to challenge and refine our cosmological models, compelling theorists to rethink assumptions about gravity, dark matter, and galaxy formation. They will inspire innovative computational methods, artificial intelligence-driven analyses, disciplinary collaboration together astrophysics, cosmology, astrobiology, and even philosophy. Moreover, these galaxies symbolize the interconnectedness of the cosmos, reminding us of our own Milky Way, and indeed is intertwined with countless interactions across billions of years. The stories written in their stars are, in many ways, our stories too, stories of creation and destruction, isolation and interaction, simplicity and complexity, darkness and illumination. In studying satellite galaxies, humanity embraces its profound curiosity about the universe, driven by a fundamental desire to understand the cosmos and our place within it. Each discovery about these small companions enriches our cosmic perspective, offering a deeper appreciation for the beauty, complexity, and wonder of the universe we call home. The Large Magellanic Cloud, LMC, a satellite galaxy of the Milky Way, is one of the most studied celestial objects due to its proximity and unique characteristics. Located about 100,000 light-years away from Dorado, it serves as a laboratory for exploring star formation, galaxy evolution, and the Its irregular barred spiral structure, distinct from typical large galaxies, offers valuable insights into gravitational interactions and the forces shape structures. Rich in young, massive stars and active star-forming regions, the LMC is home to the Tarantula Nebula, 30 Doradus, the most active star-forming region in the local group. This nebula produces stellar clusters that provide critical data on stellar. The LMC also contains notable supernova remnants, including SN 1987A, the closest observed supernova in modern history. SN 1987A presented opportunity to study the life cycle of massive stars and how supernova shock waves enter surroundings. Galaxy is composed of an old stellar population, making it a crucial subject for studying galaxy evolution over cosmic timescales. It hosts numerous globular clusters, open clusters, and variable stars, RR Lyrae and Cepheid variables. These stars play a vital role in distance scale, as their predictable variations serve as standard candles. This caliber for determining the Hubble refining our understanding of the universe's expansion rate. Research into the structure of the system reveals its dynamic interactions with the Milky Way and its smaller companion, the Magellanic Cloud, SMC. These gravitational interactions cause tidal distortions and an exchange of gas and stars between the galaxies, evident in the Magellanic Stream, a elongated structure of gas extending from both galaxies. These processes likely contribute to the irregular morphology of this satellite galaxy and stimulate its star formation activity. The composition and metallicity of the Magellanic satellite present another area of scientific interest. With a lower metallicity than the Milky Way, it serves as a valuable proxy for studying the conditions of early galaxies in the universe. Its interstellar medium is real hydrogen and molecular gas, both fundamental to star formation. Observing its chemical dust content helps astronomers model the chemical enrichment of galaxies and understand how feedback mechanisms influence their evolution. The Magellanic neighbor is also central to studies of dark matter distribution in galaxies. Since its mass is largely dominated by dark matter, it opportunity the properties and behavior of this elusive substance. By analyzing curve, gravitational lensing effects, interactions, astronomers gain deeper insights in large-scale distribution of dark matter. Observations from advanced telescopes, including the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, ALMA, and observatories, have significantly expanded our understanding of this nearby galaxy. Missions, and with the James Webb Space Telescope, JWST, promise to uncover even more details. Multi-wavelength studies, from X waves, continue to reveal of its structure. Active star formation. The Magellanic Cloud holds a prominent place in cultural astronomy. Indigenous peoples of the Southern Hemisphere have long incorporated it into their mythologies and cosmologies, often viewed as a celestial companion to the Milky Way or a distinct cosmos. Its visibility to the naked eye makes it a familiar and awe-inspiring night sky wonder for millennia. Of astrophysical research, companion bridges are understood galactic process of contact evolution. By studying galaxy, scientists uncover fundamental shaping galaxies and their providing a window into the history and future of cosmos. The Magellanic stellar system also has a fascinating star formation history. Spectroscopic and photometric studies reveal that it has experienced multiple bursts of star formation over time. Those are believed to be closely linked to its interactions with both the SMC and the Milky Way. Gravitational forces from these interactions likely triggered compressions in its interstellar medium, leading to intensified star formation. These events provide a unique opportunity to study how galactic interactions shape their evolutionary trajectories. The rotation curve of the Magellanic Disk is another key area of investigation, shedding light on its mass distribution. By measuring the velocities of stars and gas within the galaxy, astronomers infer the presence of dark matter. Observations suggest that, like most galaxies, it possesses a substantial dark matter halo extending far beyond its visible disk. Understanding the characteristics of this halo is crucial for unraveling the nature of dark matter, one of the greatest mysteries in modern astrophysics. One of the most intriguing aspects of the Magellanic Cluster is its ability to host a diverse array of stellar remnants, including white dwarfs, neutron stars, and its dense star clusters provide evidence for the formations, which offer valuable insights into the final stages of stellar evolution. Observations of X-ray binaries in this galaxy provide critical data between compact objects and their stellar companions, shedding light on the physics of accretion and relativistic jets. Additionally, the Mag cluster's globular and valuable for studying the early stages of galaxy formation. These ancient structures, among the oldest in the universe, contain stars with extremely low metallicities, providing insight into the conditions that prevailed during the universe's infancy. The distribution of these clusters also offer clues about the meteorite's past interactions with other galaxies, helping to reconstruct its orbital history. In the context of stellar evolution, the Magellanic serves as a natural laboratory for understanding how stars of different masses evolve and reach their final stages. The presence of massive stars, including Wolf-Rayet stars and red supergiants, researchers to investigate the processes leading to explosions and the formation of compact remnants like stars and black holes. The Tarantula Nebula in particular remains a focal point of study, as it hosts some of the most massive stars ever observed, some exceeding 100 solar masses. The Magellanic also plays a significant role in our understanding of the cosmic baryon cycle. Observations of its gaseous halo and the Magellanic Stream, a vast ribbon of gas extending from both the LM-SMC, provide on how galaxies acquire, retain, and lose gas over time. This is essential for regulating star formation and shaping galactic evolution. The Magellanic Stream, composed primarily of neutral hydrogen, to have been stripped from these galaxies during past interactions, serving as a potential reservoir of material that may eventually accrete onto the Milky Way. Moreover, the Magellanic Companion provides a unique study the interaction of fields and the interstellar medium. The movement of dust grains and the polarization of starlight observed within the LM reveal large-scale magnetic influence gas dynamics and molecular cloud formation. Understanding these processes is crucial for developing comprehensive models of galaxy evolution. The future of research on the Magellanic Nebula holds immense promise with the advent of next-generation observatories. Instruments like the James Webb Space Telescope, JWST, will enable astronomers to study its star-forming regions in unprecedented detail, probing the earliest stages of star planet formation. Meanwhile, radio telescopes such as the Square Kilometre Array, SKA, will map its neutral hydrogen distribution with unparalleled resolution, providing new insights into its gas dynamics and interaction history. Ground-based facilities like the Extremely Large Telescope, ELT, will further contribute by resolving individual stars within this galaxy, allowing for precise measurements of their chemical compositions and ages. As our knowledge of the Magellanic cluster deepens, it becomes increasingly clear that this nearby galaxy is central to answering some of the most profound questions in astrophysics. From the nature of dark matter to the mechanisms driving star formation and galaxy interactions, the LMC continues to yield crucial insights into the workings of the universe. The Magellanic Cloud is also an invaluable resource for studying chemical enrichment in galaxies. Its unique metallicity gradient, which varies with distance from its center, offers a window into how heavy elements are distributed. In the abundance patterns of elements like carbon and iron regions, researchers can reconstruct its history of and supernova activity. These studies are significant for understanding the origins of life-essential elements carbon and oxygen, which release into the key area of investigation. LMC's role in galaxy mergers. It continues interacting with the Milky Way, it gradually loses mass through tidal stripping. This process not only alters the Magellanic satellite structure but also contributes to the formation of stellar streams and the accretion of gas onto the Milky Way. In several billion years, the LMC, an event that will have profound effects on structure and dynamics. Studying these interactions in real time offers a unique opportunity to model the physics of galaxy mergers, a fundamental process in the hierarchical growth of galaxies throughout the universe. Furthermore, the matter's position within the local group allows astronomers to investigate how its radiation field impacts the interstellar medium. Intense ultraviolet radiation from young, massive stars in regions like the Tarantula Nebula drives powerful stellar winds that interact in gas, creating intricate structures such as bubbles, shells, and filaments. These features are crucial for understanding feedback mechanisms in galaxies, where energy and momentum from stars regulate star formation by either compressing or dispersing molecular clouds. One of the Magellanic System's most significant contributions to astrophysics lies in its population of variable stars. Classical Cepheids are abundant and have a role in refining the cosmic distance scale. Their well-established relationship between luminosity and pulsation period provides a highly accurate method for measuring extragalactic distance, helping to determine distance. Observations of these stars have enabled astronomers to achieve some of the most precise measurements of cosmic, significantly reducing uncertainties in our understanding of the universe's growth rate. This neighboring also serves as a key benchmark for studying the interaction of matter and baryonic matter in low-mass galaxies. Simulations of its evolution within the Milky Way's gravitational field suggest that its dark matter halo may be asymmetric, shaped by tidal forces and past interactions. By comparing observational data with theoretical to refine their understanding of dark matter's influence on galactic dynamics and structure formation. Additionally, the Magellanic provides an exceptional laboratory for studying supernova SNRs. The diversity of these remnants, including the collapse and thermonuclear supernovae, offers a comprehensive view of how these explosive events impact their surroundings. Multi-wavelength observations spanning X-ray, optical, and radio frequencies reveal details about explosion mechanisms, ejected material, and the influence of supernova shocks on interstellar gas. Its rich population of planetary nebulae and asymptotic giant branch (AGB) provides crucial data on the late stages of stellar evolution. Studying how stars shed their outer layers, astronomers gain enrichment of the interstellar medium with heavy elements. Observations of dust production in AGB stars further enhancing of dust formation and recycling in galaxies, processes that influence both star formation and the cooling of interstellar gas. A focal point in stellar evolution research, this galactic neighbor provides an idea for studying stars across a wide range. Its well-resolved stems offer key insights into how gas over time. The presence of ancient stars acts as a fossil record of the early universe, allowing astronomers to reconstruct its chemical and dynamical history. Differences in metallicity and age between the central bar and outer regions further highlight the complexities of galactic evolution. The gravitational interplay between this system and its smaller companion, the Small Magellanic Cloud, SMC, remains a cornerstone of modern astrophysics. Their long-term interaction has given rise to structures such as the Magellanic Bridge, a stream of stars and gas linking both galaxies, and the Magellanic Stream, a massive tail of gas trailing behind them. These formations provide an excellent laboratory for understanding tidal interactions, gas dynamics, and the stripping processes that shape galaxies over cosmic timescales. In its most active regions, the tarantula stands out as a key site for studying the formation of massive stars. Hosting an exceptionally dense population of young stars and clusters, it is often compared to the intense star-forming environments of the Earth. Observing this nebula allows astronomers to explore the conditions under which the first generations of stars formed and how their energetic feedback influenced surrounding matter. Within the nebula, R136 contains some of the most massive stars ever discovered, challenging existing theories of stellar evolution. Beyond its stellar, this satellite of the Milky Way is a valuable resource for understanding the complex relationship between gas and dust in galaxies. Its interstellar medium, rich in neutral hydrogen, molecular clouds, and ionized regions, extensively across wavelengths. Reveal intricate feedback mechanisms, where energy from stars regulates the cycling of gas and dust, shaping future star formation. The Magellanic System is pivotal in studying cosmic reionization, the epoch when the first galaxies ionized the universe with neutral hydrogen. Its low metallicity and active star formation make it a valuable prophylactic conditions. By analyzing the ultraviolet radiation escaping from its star-forming regions, researchers gain insight into how the first galaxies contributed to reionizing the cosmos. Advances in spectroscopy have allowed astronomy chemical enrichment history with increasing precision. Detailed measurements of elements like magnesium, silicon provide a timeline of nucleosynthesis events. These studies reveal multiple star-forming episodes punctuated by quiescent periods and bursts of renewed activity driven by external interactions. The chemical hints at the influence of different types, including core collapse and explosions. The Magellanic Companion is further notable for its role in gravitational microlensing. As one of the Milky Way's closest neighbors, it frequently aligns with background stars, creating opportunities to observe these rare phenomena. Microlensing events have been used to search for dark matter in the form of massive objects that rise in the system. These studies have placed important constraints on dark matter's nature while expanding our knowledge of planetary systems in nearby galaxies. Additionally, this galactic neighbor plays in understanding the galaxy groups. Alongside the small Magellanic Cloud, SMC, and the Milky Way, it forms a hierarchical system that galaxies evolve in a gravitationally bound environment. Observing these refines galaxy group dynamics, helping to interpret the structural and stellar. The Magellanic Cloud serves as a laboratory for investigating the life cycle of interstellar matter and the cosmic processes shaping galactic ecosystems. Its network of supernova remnants, SNRs, illuminates the violent deaths of massive stars while influencing their host galaxy. The